So the first rows are the best. Going upstairs is bad for your knees. Don't go upstairs. Stay downstairs. Exactly, more leg room.
You have to pay extra in the updates.
No, you don't. If he takes money from you, don't give him.
So, buongiorno Rimini. I think we're gonna start. Are you having a good time? Yes. First I remind you to mute your phones and your laptops, and to rate. And I encourage you to rate and comment the talk about it when you finish, but silently. And well, the first speaker here is Hinek. He's a classic here at EuroPython and all Pythons all around the world. He's maybe a fan of Metal Gear Solid, and well, he has promised us to we're gonna gain 5 weeks of vacation. So I take your word. No pressure. Let's give him a warm applause.
All right, hi everyone. So first of all, I'm not a fan of Metal Gear Solid. I'm just a fan of cultural references. As said, I am Hinek, and I'm here to talk about last year. About my last year, because after I've wrapped up PyCon US, which was in Portland, which is the Pacific Northwest of the US, I took advantage of being that far away from home and took the classic road trip people just do, usually in white cabriolets. I went from San Francisco down to LA, up to Las Vegas, through the mountains back to San Francisco, and a small detour to Hawaii. Now, this little tour plus PyCon took me more than 5 weeks, which means that I've been more than 5 weeks absent from work. And with every photo I've posted, people kept asking me how I do it and whether I still have a job. Now, it turns out I still do have a job, last time I checked. And in that job, I'm responsible for almost 70 projects. And it still worked out that well that I'm gonna even take 7 weeks this year when I'm gonna spend a month in Cape Town, South Africa. So let's see if that's gonna be another talk. But it also turns out that the answer is a lot longer than 140 characters. So that's how here at the airport of Kauai, with a $7 plastic cup of beer, this talk was conceived. And I'm here to tell you my story, or more like the bits of it that fit into 45 minutes and that I think are vital for my sleep. And I'm gonna touch on a lot of topics. It's gonna range from DevOpsy things, like people are usually used for me, but I will also talk about general software engineering, so there should be something in there for everyone. And each topic by itself is a talk by itself. So as usual, there will be a link at the end of a page with all the links for you to study if you want to know more about a certain subtopic. Now, with that said, let's get going. Like every big change, it all starts with your attitude. You have to start prioritizing quality, which unfortunately means that you will spend a significant time on non-features. And that brings us directly to incentives. Because nowadays everything is top priority. If you ask your manager if quality is a priority, they will probably tell you that it's the biggest priority ever. However, how are the incentives? If you do not have time to write tests, to instrument your systems, it's kind of like a construction company that claims that safety is #1 priority, but forces their workers to buy their safety gear out of their own pocket. And it's true that reliable systems do take time. And if your only performance metric is to ship new features, you may have a conflict of interest here. However, the good news is that there is a solid business case to be made for spending time on quality and reliability. And that is that the fewer urgent interruptions you have because something is going up on fire, the more you get to work on important stuff. Or if you put it the other way around, if you build a lot of unreliable systems, unreliable programs, apps, whatever, there is an inflection point where you just stop being productive because you and your coworkers are busy fighting fires all day and you do not get to ship a new feature at all. And we've seen it with a lot of startups that have a very fast trajectory and then like 2 years nothing happens. Well, this is what happens. And this is also how I ended with 70 projects, because I'm forced, because I'm a very small company, I cannot just tell other people to fix my crap, so I'm forced to build quality stuff, and it just accumulates. This, of course, takes some long-term thinking, which is sadly not too common in our line of work, and unfortunately, that is the part I cannot help you with. Yes, but yeah, let's get more practical. So the first thing, I'm going to defer to authority, and no one less than Tony Hoare, who gave us Quicksort, who is quite accomplished with all things concurrent systems. And what he says is the price of reliability is the pursuit of the utmost simplicity. And if you prefer a Dutch sage, which at a Python conference is completely reasonable, then Dijkstra said basically the same. So you need simplicity, otherwise there will be no reliability. And at this point it's important to stress that you must not conflate simple and easy, because easy solutions usually are not simple. An easy solution is usually a hack. And simple solutions, like solutions that will serve you well in the long term, are usually not easy to find. And I find a good way to approach simplicity is from the other side. So let's talk about complexity for a moment. So complexity in software is something I would say is the number of concepts you have to keep in your mind when you are trying to reason about the behavior of a system, of a program, of a piece of something. And especially how many things you have to keep in mind when you're trying to reason what happens if you change a little corner of a system. And humans are naturally limited in the numbers of things we can juggle, both literally and figuratively in your mind. And if you have too much things going on, too many balls in the air, you start dropping things. And that's when normal accidents happen. This term has been coined by Charles Perrow in the wake of the 3 Mile Island incident, which was a nuclear power plant incident in the United States. And it's called normal because they are inevitable in extremely complex and tightly coupled systems. Now, if your program is a contraption like this, it's impossible to reason about changes. What will happen if you play with this knob? It's impossible to tell. And what breaks if the part with the knob breaks? I would say it's impossible to say, but actually it's very easy to tell. The whole thing is going down in flames. That's the problem of having tightly coupled complex systems. Now the irony is that if you try to make this thing safer, you're adding more complexity. What does it mean? The system is more likely to fail. So you cannot fix a system or a program that looks like this. You can only rewrite it from scratch. Now when we are talking about complexity, we have to differentiate between 2 types. The first one is the essential complexity, which is the good complexity. That's the complexity your customer or your boss is paying for you to solve. It's inherent to the problem you're solving. The other one is accidental complexity. This one comes from using wrong abstractions, having cumbersome deployment procedures that stop you from deploying, or just using ancient and inadequate tools like Python 2. Yeah, I cannot drop this mic, so. So, obviously, only in a perfect world you can work only on essential problems. But still, you should always keep in mind, what problem are you solving here? Is this essential or is this accidental? How is your ratio between those two? Now, what is simple software? And that, of course, is a talk by itself, if not a conference by itself. But given we are in Italy, I really like the ravioli metaphor. Now, given that normal accidents happen in tightly coupled and complex systems, it follows that you should prefer to have simple objects that are self-contained and that have simple relationships, just like ravioli. Because if you look at it, they are small, they are self-contained, nothing is leaking out unless you overcook it. And I heard in Italy there's jail time on overcooking pasta. Yes. That's an adequate thing to do. Now, in other words, your objects, your functions should do as little as possible, but more importantly, it should know as little as possible about other objects and other functions. And this gives them a clear interface, which you can program against, and the few assumptions help you to have simple relationships. Because, as many object-oriented mentors said before, dependencies will kill you. And by dependencies, I do not mean things you install from PyPI. Donald's stuff is doing great work, install as much as you want, but dependencies between your objects. And especially, I really like to not have bidirectional relationships, which are almost always bad. And I like to think of an object graph like a family tree. If you have loops in your family tree, it's a bad sign, right? So think about your object graph similarly. Now, all of this, if you follow that, gives you system components that are really easy to test, because you have clear interfaces that you have to either fake out or mock or whatever you're doing, and it's few dependencies. This is good. Now, bad designs, staying on a pasta theme, is the opposite. It's big classes, also known as God objects. And a God object is an object that knows too much and that does too much. And those are obviously very hard to test, because just to instantiate such an object, you need a dozen of other objects. And you get yourself to fight accidental complexity really, really fast. The sad thing, though, is that God objects are pretty common in the Python ecosystem. And the reason for that is that writing classes in Python is a bit annoying. But I will touch on that later. Another mostly self-inflicted complexity is basing your design around subclassing. Or as Corey puts it, you will regret it. And I'm not here to hate on subclassing per se, although I think it's well known that I personally try to avoid it. But subclassing is subject to a lot of misuse. So if you think back, what subclassing has been invented by its inventors for is specialization, not code reuse. If you're doing a subclassing for code reuse, you're kind of making the inventors of subclassing sad. So don't do it. And there's a bunch of rules around it, like Liskov's substitution principle, the open-close principle, all these things. And if everyone followed those rules, there wouldn't be any regret Corey is talking about here. And it takes actually a lot of experience in design and modeling to do subclassing really well. Now, the thing is, subclassing makes your software always more complex to understand. It's easier to write. It's less typing, no question there. But it is harder to understand because you end up with namespace confusion. So where is this attribute coming from? Can I name my attribute like this, or is there some attribute up there in an inheritance tree that has the same name, and everything will break? You have to understand the MRO. Your logic is not only distributed in one level, like one method calls the other. No, you have to traverse hierarchies to understand where your calls are going through. So this is all not great, but it is about making trade-offs. So I'm not saying you must never subclass, but you should be aware that, that you are doing a trade-off here between easiness and complexity. And more importantly, this is not where you should start. So a subclassing may emerge as part of a design out of practical reasons, but it shouldn't be the thing you build everything on. And so don't start projects by inventing hierarchies. And as a reminder, many new and modern languages that came up in the past years, like Go or Rust, are doing just fine without having any subclassing at all. And I'm gonna say that Swift only has subclassing because Apple needed to ensure compatibility with Objective-C. So, relatedly, meta classes, very powerful, often overused. They're a bit of Python's monads, because people tend to read into them, then they find them interesting, and then they write a blog post explaining everyone how great and simple it is. But it isn't. You're again paying with complexity for mostly syntactic sugar. So leave them to David Beasley. He will do something nice and depraved in his evil lair. And everyone is happy. So just to be clear, I'm not talking about abstract base classes here, which are a meta class and subclassing. That's just the way they are used, so that's something different. Although I personally prefer the approach of the ZOP interface, which uses class decorators for it. But yeah, ABCs is not what I meant here. Now, I mentioned that writing classes is tedious in Python. So I decided to do something about that. And I wrote address. How many of you have heard of address? Okay. It's getting better by the year. So those whose arms stayed low are probably restless in your seats, dying to tell me about name tuples, right? So turns out I do know about name tuples, and maybe I know too much about name tuples. And it's also such a thing that people discover them and then start tweeting out that it's the best thing since sliced bread. So first of all, that's a low bar, because carbs are really bad for you. But other than that, name tuples have a history. At least that's what I've been told by some ancient Python sages. They were made for the standard library if they return a tuple, so they can attach a name to the tuple, so it's more readable. It makes sense, right? Named tuple, tuple with name. So, and they're great for that. But they are terrible as a class replacement, because then you end up with the tuple type in your inheritance tree, which means that you have very odd rules for equality. You have accidental iteration. You can accidentally unpack your class, which gives you very weird errors and yeah, bugs, which don't make any sense. Or you want to attach a method to a named tuple, well, you have to subclass it. You want to influence the initialization, have fun implementing dunder new. So, but people do it because it's convenient. And that's why I wrote address, because name tuples, if you ever wondered when to use them, it's very simple. You have a tuple and you want to attach names to it. You use a name tuple. Other than that, write a class or use address, which will write the class for you. And it has many more goodies like validators, converters, default values, including factories. So for the few poor who didn't know about it, check it out. And you may be asking, Hinek, is this a serious project you should put into production? And I'm so glad you asked. Yes, it is. I have stickers. Get them. Now, moving on. Operational complexity. Which is the complexity of running your infrastructure or parts of infrastructure. And I think it's not controversial to say that distributed systems are hard, right? Now let's look at a very, very simple one, which many wouldn't even consider a distributed system. We have a client that speaks to a content delivery network, which is not part of your infrastructure. We have an application that has a work queue, Celery, for example, a database, and a Redis cache. So far, so standard. Many run something like this, I run something like that. Now, the problem here is that every box you have there is a point of failure. If any box goes down, the whole thing is down. But wait, there's more. Every arrow between those boxes is a point of failure too. So in this case, you come up with 10 independent points of failures, which, if you know something about probabilities, they almost add up. And the reason is simply that network partitions are a thing. You may live in denial because it never happened to you before, but it will hit you too eventually. So it's better to accept your fate and learn from others. They are kind of rare if you don't run at at a huge scale, but especially if you run at scale, rare occurrences are kind of common. Now, all I'm saying is think twice before you add more boxes and more links between those, because each of them introduces new, exciting ways to fail. And with that in mind, let's talk about microservices. Microservices is about splitting up an application in many small web services. There are many great reasons to do that, but you end up with many more red boxes and many more red arrows between them. So your big monolith that has certain annoying properties we all know about ends up being a highly distributed system, which you may or may not be equipped to deal with well. Because now you have new decisions to make. For example, are you going to go for this tangled mess, which is so tangled that I was too lazy to make the slide myself and took it from Andrew Godwin? Or are you going to use a message bus? What message bus? And all the new problems that come with it, like service discovery. You cannot really run this without service discovery. Which service discovery? Aggregate logging. You cannot just look into files anymore. Tracing. You shouldn't even think about microservices without having a distributed tracing in place, which, by the way, I heard there will be a talk later today about it, so you should check it out. And of course, all the other fallacies of distributed systems that we like to forget and that come back and bite our butts later. Now, what you really want and what you really need are boundaries. You want to define and adhere between your boundaries between your modules and your packages. That's what you really want. You do not need a network between your classes, okay? And then you can have also separate teams working on separate parts if you have clear interfaces. And once you have that, it's very easy to graduate into microservices because the boundaries are already there. Now you just put a network between them. And there is a place for microservices if you need to scale out, because as we know, we have a thing called the GIL in Python, which is kind of annoying. Or if you live in a heterogeneous environment like I do, I need to interface PHP and Perl, so web services it is. Now, in that vein, I need to stress that complexity is not the devil by itself, but it's a price you pay to get things done. So you should more consider it like a currency, but you have to be conscious of your budget, because the budget depends entirely on you, on the time you can invest in running something, and the human resources you can throw at this problem. And the price can be quite high. So if you take, for example, Kubernetes, which is an amazing product, but it's super complex to run. It's easy to set up. I've set it up like 5 times by now, and it's really, really easy. But do you really know how to keep it running properly? With all its etcds, flannels, Prometheus, Docker, each of these parts are pretty complex by themselves. So if you can afford it using your complexity budget, great, get it, run it, put some people on it. But if you can't, if you put tech in production you don't master because it looks cool, Dante has some opinions and predictions about your immediate future. Now, speaking of stupidity, this is obviously an hyperbole because things only seem stupid in hindsight. But people tend to act stupid. I tend to act stupid. Just today I forgot my wallet. But you act stupid for good reasons too. For example, if you're sleep deprived because you just came over Atlantic and are jet lagged, or the baby cried all night, or you're at a busy airport on your way to a conference and need to quickly deploy a hotfix, or you're hustling really hard to satisfy some well-meaning venture capitalist that has the best intentions for you and your future. Now, I have opinions on that, and my opinions are the same as the one of John Allspaw, the CTO of Etsy. I don't believe in human errors. I believe that if a human causes an outage, it's a system that failed them. And if you remember the big S3 outage earlier this year, there was a great post-mortem written by AWS, and you should really read it. Like any post-mortem is worth reading, but this one is also very good. And it turns out that a human used a tool the wrong way, and it took down half of the internet. Now, the post-mortem doesn't focus on that. It focuses on the tool and how to prevent this from happening again. Because people make mistakes, and it's your job to prevent them from doing that. You need to protect them. Now, when building tools and APIs, you should always assume that the operator is drugged from the dentist, consoling a crying baby, or is just sitting in a boring conference talk. There are many reasons to be distracted from the thing you do and still need to do it, so take it into account. It's kind of like products for people with physical disabilities. It always turns out that those products are better for everyone. And that's true with this just as well. And if it takes just one click or one API call to lose all your data, someone will make that click and will make that API call. Maybe they were just cleaning their phone and just hit it by accident, but they will do it. There was other day, there was the story of a junior developer who kind of accidentally dropped the database of some startup, and he got fired, and the CTO was threatening him with legal action and everything. And it turned out that setting up a development environment consisted of running a bunch of commands. You had to copy and paste from some document, and you have to replace passwords and usernames. And if you have sharp edges like this, it's your fault if people cut themselves or cut your company. So in this case, they should have fired the CTO right away. But yeah, you know how it is. Anyhow, part of that is how you handle input. And it doesn't matter if it's, the input is maliciously broken or by mistake, you still have to be careful about what you let in. And I fundamentally disagree with Postel's law here. I think you should be conservative in both what you send and what you receive. And this, by the way, was neither malicious nor a mistake. It was literally the only thing I liked about San Francisco. Now, invalid data. I like to think of it of a time bomb. And I'm talking about things like an invalid date string, for example. If you have something like that, you let it in your system, it starts wandering through your system. And the deeper it gets, the more damage will it cause. And the sooner you catch it, the better can be your response. So just for an example, you let the user give you a date string. If you catch it ideally in the browser, you can tell the user, okay, this is wrong, you have to do it like this. If it reaches your ORM, you will probably show, you will get an integrity error and the user gets a 500. That's not good. Other edges are, of course, your dunder init or command line parsing. So, validate your data at the edges? Almost. I think validation is not enough. I think you should always strive for a simple canonical form of your data that the rest of your system can rely on. Because your business code should not know what even JSON is. It should just take dicts or other native Python data types. Or if you know the structure of the data, it should actually use a class. And I find that the decision between classes and dictionaries is actually pretty simple. If you don't ever iterate over the keys of the dictionary, you probably should use a class. Because a class is much better at catching typos and other little accidents while developing it, while dictionaries make sort of work and just shadow some mistakes for you. Now, passing strings around in general is also not great, because if a function takes a string, it becomes a parser. It might be a simple parser, but it's still a parser. And parsers are not that simple, and if they screw up, it can be really bad. So I don't like strings in APIs at all. So, and if you need a symbol or something, in Python 3.4 later, we have enums. And there's also a PyPI package that will give you the same classes, and they are great. Now, I could keep talking and talking. However, given that complexity leads to normal accidents, and computers are kind of complex, right? And distributed systems are kind of complex to the second. It kind of follows that failure is inevitable. Everything I told you before is about minimizing risks, and you should do it. But eventually something will fail. So if you work in computers, failures are part of your life, whether you like it or not. So in practice, your reliability will land on a spectrum. Somewhere between Twitter in 2007, which had 98% uptime, which means a downtime of 6 days, and NASA in 1969, who landed on the moon, despite a human error on descent, but the software was robust enough to compensate for the stupid mistake of the astronaut. And I think we can argue that astronauts generally are not stupid, and yet they make mistakes. Now the problem with NASA-style reliability is that you need an actual genius to write your software, a genius that will just invent software engineering on the side while writing the moon landing software. No big deal. So you might have to scale down your expectations unless you have Miss Hamilton on staff. In that case, I would like to apply for an internship. So failure is inevitable. All you can do is minimize risks. You can prepare for it to happen, and then you have to deal with it. Don't ask me how long it took me to get this done. And I'm gonna give the rest of the talk away right now. A long vacation is the result of good failure containment and solid recovery. And let's shift gears here and talk about that. So you've embraced failure. How do you expect failure? So if you need a system or a program do anything reliably, then you need to monitor it. It's that simple. Because for all you know, it's down. If you need to have confidence on it working, you have to monitor it. And so you need to check for outages, you need to instrument it, you need to instrument your system, and you need solid error reporting, because a silent failure is terrible. I've talked about these topics in the past 2 years. My taste didn't change at all. I still love Prometheus for instrumentation and monitoring, and I still love Sentry for error reporting. Full disclosure, David Kramer may or may not have a video of me singing Beyoncé in a karaoke bar in Bilbao. But both is open source. Sentry has reasonably priced paid plans, which you can scale in or scale out to, so there's no lock-in either way. Now, your code. How do you expect failures in your code? Well, if it's local, it's simple. You just try accept, and that's it. Remotely, you're lucky if it's that simple. Because instant errors are rare and fortunate, like connection refused or a 500 or something like that, where you know immediately, okay, something's going wrong. The worst failure scenario is that nothing happens. So whatever you do remotely, you have to put a timeout on it. And one missing timeout in a database driver was enough to ground an entire American airline once. So always put timeouts on it. Now, if you have a timeout, what do? You've just hit a timeout. Do you carry on like nothing happens? That gives you very slow, very useless requests. It's a bad experience for users because they have to wait 30 seconds to get a 500. And it's giving more load to a system that might be overloaded. And for that, there's a circuit breaker pattern. How many of you have heard of it? Okay, I'm gonna make it really quick. It's very simple, very useful. So, it's kind of a local proxy between you and a remote system. And in a normal state, it's closed, like a drawbridge, okay? So the requests go to the remote API, the results go back. Simple. Now, if something fails, it doesn't have to be a timeout, but a timeout is the best example for that. And it fails more than once, because In distributed systems, let's face it, things fail once all the time. So if you have a certain amount of failures, it will switch from closed to open, and the requests have to wait, like at a drawbridge. And at this point, it starts ignoring the remote system, and it's just giving errors back to the client very, very fast. So, after a certain time, it will send out a probe, one lucky request from the client to check whether the remote is still broken. And if it succeeds, well, great. The drawbridge is closed again. Everything is like before. If it fails, well, it stays open, and we will try again later. This is very simple, very effective. Now, I've said that adding more components to a system is usually bad. However, if it's the same component, and if you hide it behind another component that is way more reliable than your crappy code, then it might become something good. So for example, if you take something like HA proxy, which I don't say lightly, is very good software. It's a piece of software that never let me down. So if you put multiple of yours and protect it with HA proxy, your reliability is actually going up. And in military, they have this saying that 2 is 1, 1 is none. So meaning you should have at least 2 of everything. And if something is really, really important, you should have 3 of them. So you never even get into the situation that you have only 1 of something. Now, this principle made the internet almost unbreakable, unless everyone uses the same DNS provider, or unless everyone uses the same storage system in the same region, including the monitoring panel of said storage service. And this works at any level at the network. You should have more than one switch, more than one uplink. You should have more than one server. You should have, well, more than one data center. That's like level up game. Not everyone needs that. But you certainly should have more than one backup. Because if this is all it takes for you to lose your data, you do not have backups. And also, if you do not test your backups, you also do not have backups. Ask GitLab. They have a story to tell. Now, if you want to be dispensable, you must not be a knowledge silo. So if people ask you something regularly, write it down. If you have regular tasks and standard procedures that cannot be automated, write them down. And if you have something that needs to be done in case of emergency, write it down. Thinking that you will remember it when you need it is a very dangerous fallacy. And it has been a staple of aviation security to have a checklist for everything, like literally everything. Ask any pilot. And having a contingency plan you can stick to if shit is hitting the fan is priceless. You can believe me. And this can be also communication. It doesn't have to be something you do. It can be something you tell someone, like your social media team, so they don't lie to your customers that everything is dandy and they should start to reboot their computers or whatever. So, finally, how to deal with a failure in your application. Well, your database is gone, a web service is returning invalid data, or the infamous timeout. So first, failure containment. Don't make it worse. Because cascading failures can happen, and that means that everything just melts under you, even completely unrelated systems. And in relation to that, let's talk about something very simple with a very big impact, and are retries. Retries are essential in distributed systems, because as you've seen before, transient errors are completely common, so you have to take them into account. But they're also very, very dangerous, because if you use them loosely, you can DOS yourself. Or even worse, you can DOS a third party, which can mean that you land on a blacklist, or you get even into legal problems. So what do? You back off. But how long do you back off? If you just run into a deployment or a packet got lost or whatever, 1 second is fine. If a system is overloaded and you're just waiting for your scheduler to provision more servers, 1 minute may be adequate. And if there's like a hardware failure, maybe a switch and some poor schmuck has to go into the DC and replace hardware, well, every 5 minutes just check if if he or she has done it, and try again. The trick is to do all of it. You try with a very short period, which you then raise exponentially. And this is pretty good. But there's still a problem, because if all your services do it at once, you still have a lot of load in the same moment. And that's where a jitter comes in. A jitter is just a random number that you add to the computed exponential backoff, and it will space out the retries between your systems, so you don't get this thundering herd. Okay, so this is intuitive, I think. But let's dig deeper. Let's say you have a policy of 3 retries per client click, whatever. And let's assume that the back end is your responsibility. And because you read the orange news page, you want microservices. So let's do it. So at this point, one request in the front end, like a 1 click, means 9 hits to backend A in the worst case, because 3 times 3. But we are not even close to microservices. Let's add one more layer, and you're DOSing yourself again. This is called the combinatorial retry explosion. And 1 user click means that C gets hit with 3 times 3 times 3, 27 requests. Now imagine if C was slightly flaky because it was overloaded before. Now it's toast. And the simplest solution, the one I use, is that you retry only at the top, like in the client. But this only works if you know where your top is, which may or not be true. And then you have to do something more complicated, like per request retry budgets. But then you have a state that has to wander around with your requests. And that's not that simple anymore. And this is a good example for complexity through microservices, because such a problem just doesn't exist in a monolith. And there's a lot more to be said. Back pressure, have a way to signal to the app that you are overloaded. Unbounded queues, do not have them. It's mathematically proven that an unbounded queue is worse than no queue at all. Do not use unbounded queues. And there's a bunch of links on my page to that. Now, next one, insight into failures. If something fails, you want to know what happened and why did it happen. Because nothing is worse than a silently failing backup script. Again, ask GitLab. In the best case, you put something like Sentry into it, but at least send an email if something doesn't work. And this is true in code too. And if you do something like this, especially in libraries, I have a lot of opinions about you. Because how am I supposed to debug this? I have no chance. The same is true if you do something like this, what I like to call a vanity exception, like an exception that is special to your very special library, very special application. The error detail is still lost. Don't do that. Instead, do exception chaining. So this is the Python 3 syntax. This will attach the original exception under cause, and you can introspect what actually happened. If you're using Python 2, you have my sympathy, and there's a function called raise_from in the 6th library, so you can use it too. But really, if you do not know what to do about an exception, just let it be. Chances are that the user knows how to cope with it better than you do deep in the guts of an application. So the next one is a bit counterintuitive. If your application is unfit for work, like the classic thing is that your connection pool turns invalid because this database server has to be restarted. You could start adding complexity to reconnect the pool, but only in one thread and serve some intermediate error to your user, or you just add one line. And more often than not, this is just fine. And it also runs sys.exit also runs your add_exit handlers, which means that you get to clean up properly. And this is called crash-only software. And it's not something I just made up. There's solid science behind that. There's a lot of papers which you should read. And there's a bit more nuance to it, like micro reboots, but I found them a bit hard in Python. So, to sum it up, fail fast, fail loudly. A crash is always better than a hang. As a user, I prefer a 500 over waiting for 30 seconds and get a timeout, or then an error. And depending on your audience, you can just present a stack trace too. For example, Redis takes it to the next level. They have, if they have a crash, they show you a stack trace. But because most of the crashes are caused by faulty memory, they will also run a fast memory test to tell you that your memory is flawed before you open a bug on their, I think, GitHub. So once you have that, you need to focus on recovery. And this is where the MTTR reigns supreme. The MTTR is the mean time to recovery. And if you've accepted that failures happen, and maybe started writing crash-only software, it becomes much less important that something goes down, and it becomes much more important that it comes up fast. And that's why humans cannot be allowed to restoring your servers. Because if I pull the plug in your DC, your infrastructure starts getting up, and a lot of systems need hand-holding to come up. How do you choose? No, this has to happen on its own. And the prerequisite for that is that your app does not expect what's there, like the database. You try to connect. If it doesn't work, you try again, again, again. Maybe you just crash if your process manager allows you to add backoffs. But I just use loops and backoffs. Now, what is the secret to a long, undisturbed vacation? Apparently, $9 Mai Tais in plastic cups. But also, more practically, what you can do about it, build fault-tolerant systems that recover autonomously and throw your phone into the sea. This is the promised link. The QR code will bring you there too. Follow me on Twitter, buy your domains from Variomedia. Thank you very much. Yeah, I'm not taking questions. I don't have any time anyway, but come to me and talk to me anytime. I'm happy to discuss anything. Also, stickers.
Hoffman, and well, he's been with Python for 10 years, and he's the guy that make PyCon in Deutschland possible. So he's going to speak about Microsoft Azure and how and why is it very good tool to make services of artificial intelligence and machine learning. So warm applause to Peter Hoffman.
Thank you. Okay, so my name is Peter Hoffman. I'm a software developer at Blue Yonder. We develop machine learning algorithms for retail. So, for example, we calculate optimized price decisions for online retailers, or we calculate future demand for retailers and implement replenishment on top of it, so that the stores of the retailers neither go out of stock or have too much waste. So that's, we do this with machine learning, and most of our stack is Python. You can contact me via Twitter or on the conference or on the social event if you have any questions, and the slides will be available on GitHub under our company account. I'll show the link to the slides again at the end of the presentation, so yeah, you can take your notes. So maybe before we start, who thinks Microsoft is a really cool company that knows about open source, embraces Python, and is really fun to work with? Okay, nobody, one hand. So probably that's the same I thought. I've been an open source guy for all my life, and we have been self-hosting our infrastructure at Blue Yonder for all the time. We have a 3-digit number of servers, and sometime our CTO came to us and said, okay, we want to move to the cloud, and we started evaluating AWS, and everything went fine, and we thought, okay, let's go to AWS. It's the cool cloud provider. Every cool company is going to AWS. And then some months later, he came again and said, okay, now we are going to the cloud, but it will be Microsoft Azure. So at first I thought, oh no, now I have to administer a Windows server, I have to learn PowerShell, and I lose all my open source knowledge and all this stuff. But it turned out to be quite different. I've learned a lot in the last half year. We have started to migrate all of our infrastructure to Azure. We are following a shift and lift approach. So in the first place, we are just using the basic resources of Microsoft Azure, that's storage, networking, and computation, also virtual machines. And once we are done with the initial migration, we are moving up the stack and are using much more sophisticated services like managed database services, HDFS services, or even the managed Hadoop stack. So I've quite learned a lot about Microsoft in the last half year. I think they've changed a lot. Probably they are still not the coolest open source company, but they really embrace Python. They treat Python as a first-class citizens in their stack. And I'll show you in the next 20 or 30 minutes a little bit how we deploy to Azure and what we've learned from our deployments. So what is Microsoft Azure? Microsoft Azure is a cloud infrastructure provider from MS, and it's basically infrastructure as a service. So you give them money and you get infrastructure. It's a little bit the same with our ops guys. We gave them money and they build us the infrastructure. But the turnaround cycle with our ops team was about, I don't know, 2 to 3 months. Until we have to buy the servers, you have to put them in the rack, you have to put the cables in there and get all the software on it. So you have really long cycles if you just want to try something out or want to scale up. With infrastructure as a service, you probably have an API and you can get servers with one click, get lots of them, and once you are done with testing things out, you can throw them away. So you are much faster, and which really helps you to grow as a company. You see here the Azure dashboard. That's their UI, how you can work with Azure. You can click servers, virtual machines, all the stuff. But once you are beyond the initial phase with trying out stuff, you don't want to deploy your infrastructure via UI. You want to use tools and in the best way a declarative declaration of your infrastructure that you always can deploy it again and probably can deploy the same version of your infrastructure in a testing environment, and so you want to automate all this stuff. So now I'm going to show you how we automate it and how we learn what we learned about the tools that Microsoft provides. Before we start, I'll tell you a little bit about the architecture of Microsoft Azure. So the basic concept in Azure is a resource and resource providers. For example, virtual machines are resources, and the resource providers takes care that you can call an API and you get the resources that you request. So for each different resource, you have a different resource provider. So for virtual machines, computation, storage, or higher level services, and they all fulfill the resource provider contract. That's a standard API, how you can interact with Azure. And on top of the resource manager, you have different tools like the portal, like a CLI command, or a Python client library, or even the plain REST calls, how you can provision your infrastructure in Azure. Mostly we have used 3 different deployment options. The one that we don't use is the Microsoft PowerShell. The next one is ARM templates. That's a declarative deployment option. And then you have, on top of the REST API, Microsoft ships you Python client libraries, and you can talk to them via the Python API or via the AZ command line client or via Ansible. A really nice thing is that they use Swagger for all their API definitions and JSON schemas for the content of their APIs or for the payload. So beside Python, they support Java, C#, I think PHP, and they all generate the client libraries from the same Swagger source definitions. So you will always have the same version of the client libraries in the different programming languages. That's really nice because with this approach, Python is always up to date and on par with the PowerShell library. Another basic concept of Microsoft Azure are the resource groups. You can group your resources into a resource group, and you should do this you could of course put your whole infrastructure in one resource group. But it's better to put your resources in different resource groups based on your deployment lifecycle, because normally you will always deploy a whole resource group in a complete mode. And you want to not, if you just want, for example, to update your storage accounts, you don't want to update the whole infrastructure, but just the resource groups that you're interested in. On the left side, you see a sample definition of a DevPy server. That's a PyPI compatible internal repository we use. So we have an availability set and a load balancer, and then we have some network interfaces, again, storage account and virtual machines. And that defines the whole service internally, and you can use this resource group or the definition of the resources in this group to deploy this service in production, in development, and in testing. What's important and what's a really complex topic in Azure is the role-based access control. So for each operation you can do via the command line or the portal, you can have a role-based access control. So you, when you first create the Azure account, you are kind of super user, and you should really, as soon as you have this account, start adding other accounts and drop your privileges and give the deployment accounts just the privileges they need to deploy their resource groups. You could even say some users are only allowed to view the resource groups to see what's inside your infrastructures, and others are able to deploy it. You should really take care of this because it helps to prevent errors. That's, for example, what happened to me. I just wanted, in the beginning of our migration project, I wanted to deploy a resource group, and I missed that there was still a storage account in it, so I deleted it, and all the data was gone. In principle, I shouldn't have been able to do this, because this storage account was not my business, it was not my service, but we weren't that far with role-based access management, so I could delete it, even if I shouldn't have to do it. So what we are using as the primary deployment option is ARM templates. ARM templates are a declarative JSON-based description of the desired deployment state. It's a JSON document, and you submit it to the Azure Resource Manager, and the Resource Manager takes care of the parallel provision of the resources, the rollback, and the deployment. At the bottom, I've shown you the simple command line interface, how you can deploy a resource group. You always have to tell Azure which resource group you want to deploy, the name, and the template where you define all the JSON stuff. You can deploy a template to different regions, different services, and you can define multiple resources in one template. But each unique resource only can live in one template. You have two different deployment options. It's always either complete or incremental. If you do an incremental deployment, the Azure Resource Manager will only add new resources that are in the new template, but will not delete stuff. That's okay for trying things out, but on the normal way you want to do the complete deployment, where the Azure Resource Manager also takes care that it deletes resources that are not defined in your template, because you always want to have the declarative state that is in your template to be the one that is deployed on Azure. So what does a minimal template look like? You always have to link to a JSON schema of your template. You have to give the content versions, and then you can specify resources, parameters, variables, and outputs. Microsoft has open sourced all the JSON schema definitions for the different templates, and you can go to GitHub and really see what kinds of values are allowed in your template for which resources. So let's define a sample storage account. That's a single resource. Again, you have to tell the resource manager which type you want to deploy. In this case, it's Microsoft storage account. You have to give him the API version you want to talk to. So for one resource type, there are always different API versions you can use with different parameters. You have to tell in which region, West Europe, US, Asia, you want to deploy your resource, and then some specifics about the resource. In this case, it's just the type of storage account you want to deploy, locally redundant. One thing we learned pretty soon and use very extensively is tagging of resources. So for each resource, you can apply a number of tags, I think up to 250. And you can later on use the tags for grouping, for example, in billing or in monitoring. And once you have you're going to have a larger infrastructure with, I don't know, 3-digit number of servers, it really helps to see which service is responsible for which costs, or in monitoring to see which service fails. So my advice from the beginning, think about a tagging scheme and really apply tags to all your resources. The ARM template is not simply a JSON template or a JSON file, but you can use within the JSON file in the value parts, you can use the ARM template functions. So each time you use the bracket notation, you basically call a function, and during deployment, the result of this function will be replaced in the template for the rollout. For example, the storage accounts in Azure, they share one big namespace through all customers. So probably if you take the name test for your storage account, you can't deploy it because it's already used by some other guy. And you can here use this Unix string function, together with a resource group ID, and it will generate you a unique ID that only you use, and with this you have the unique name in the global namespace. Another one is you already specify in the command line client to which region you want to deploy, and with the with the resolution resource group location, you can get this value and don't have to type it again and again. And now you also can use this template to deploy it in different regions without changing the value of the location. You have lots of different functions at hand. You have array functions where you can use the first or the last value of an array. You can get an index of an array, the length of an array. You have numeric functions to do basic calculations, and you have some string functions that you can use in the templates. Another pattern you can use in your templates is the use of variables. So as soon as you need to use one variable more than once in a template, you can define a variable with the storage account and then can use it throughout your template. In this case, we are defining a storage account with a name, and then we can use the variable in the computation to attach the storage account to a server. And the third thing you can use in templates are the outputs. So for each variable you generate inside the template, you can define an output so that once you run your template on Azure, you can see what the actual value, once it is evaluated, is in your template. To use resource template in different stages. In our example, it's we always have the test area, then a staging area, and then the production area. You want to inject into your template external values, and you can do this with parameters. So you define the parameters you want to use in your template. You can use it in your resources, and once you want to deploy it, you can specify an additional parameters file where you actually provide the real value. So you have one template and different parameters file, and with this you can deploy it in different regions or in different staging areas of your infrastructure. What we've also learned pretty fast is don't put sensitive data into templates. So Microsoft Azure provides ways to inject sensitive data into your templates without having them in your Git repository and in plain text. So they have the secure string and secure option type objects. They have runtime retrievals within the template function for the secure type objects. And you can also reference the key value secrets. So you can, in Azure, generate a key vault with secrets, and then you can use it in your templates. And in production, always turn off debugging and logging, because it could also dump out your secrets. For rather simple deployments, the Azure resource is pretty okay, but for complex ones, it's really fast gets out of hand, because it's not just a JSON file where you define your resources, but you have also content versioning for different resources. You have parameters and variables. You have inline template expression language. You can also link templates together. So it pretty fast gets pretty hard to edit all these templates by hand. So we have pretty soon come to Visual Studio, which supports the Azure Resource Template syntax, and you have auto IntelliSense and highlighting, and it makes it much more easier to really edit these templates. We have also tried to put some Python libraries around the templates and generate the stuff, but that didn't work out that well. So at the moment we still edit the templates by hand, but with a powerful tool like Visual Studio. So how do you actually talk to the REST API from Microsoft Azure? Microsoft provides a command line interface. The command line interface version 1 was built in Node.js, but as the Microsoft guys told us, that didn't work that well. because with the command line client, they want to target Linux admins and users from the open source community. And the Node.js clients just didn't behave like the tools like you expected in this Linux server community. So they developed the CLE version 2, and they developed it in Python. It's a really nice command line interfaces with auto completion and nice documentation and different output formats. It has support for searching via GMS path, and it's also fully generated from the Swagger definitions of the REST API. So you're always up to date with this command line client, and it really helps you to work with the REST API. Yeah, for example, you can tell the ASA command line client to list you all the storage accounts inside a resource group, and then you get back a JSON document with all the information. That's fine if you want to use it to pre-process it in Python or some language that understands JSON, or even pipe it into JQ and then select just some values. But you can also use different output formats. So for example, you can dump it as a table. The command line interface uses the tabulate library. That's a common library in Python to dump tabular formats. Or you can dump it as tab-separated values and then call your org script to get the data out of it. So it really fits well into the command line chain on Linux. As I said earlier, you can also use James Parse, the query language. So for example, here I just want to list all storage accounts that are a standard RRGS from the name. And you just want to have the name and the endpoint of the blob. So that's really nice to interact with the API. We use Ansible exclusively in configuration management to provision and deploy our server and services. And we also thought it was a good way to use it to provision our stuff on Azure, because with this ansatz, we don't have to have duplicate configuration. For example, we have network ranges or host names, and you have to define them in the Azure template, and we also had defined them in our Ansible scripts. So there is an Azure RM module for Ansible, and we are using this to interact with Azure through Ansible. So there are 3 ways how we use it. We use it to deploy the ARM templates with Ansible. There is the possibility to generate resources directly via the REST API, and we use it as a dynamic inventory script to bridge the server and services into our other Ansible scripts. Simple Azure deployment is pretty easy. It's not that different to the command line client. So at the bottom you define your resource template. You can also define some parameters that you want to use in the resource template. You tell Azure which resource group you want to deploy, in which location, and you have the same deployment modes as I said earlier, the complete and the incremental deployment mode. So that's pretty the same than the command line client, but what it really helps us using the parameters from within Ansible, there we can use the same parameters that we use elsewhere. Instead of providing a template file, you could also use the Azure RM mode for Ansible to specify the resources inline Ansible. This works quite okay for simple resources like computation, storage, and networking, but for the more sophisticated ones, there's still no support in Ansible for the Azure modules. Yeah, that's what I said. There's only support for this for services, so we'll still stick to the resource templates. So this is a little more complex example. So we are using the resource manager with Ansible to deploy a virtual machine. again, you have some parameters where you tell it which size of machine you want to deploy, which storage account you want to use, the initial SSH key set up, and in which network you want to deploy the machine. Microsoft offers quite a range of Linux distributions which you can use. So in this case, we just say, okay, give us the latest Debian 8, and you'll always get an up-to-date version. If you deploy lots of machines, it probably helps if you tag them right, and then you can use the Ansible dynamic inventories feature to pull the actual information from your deployed infrastructure and feed it in your Ansible scripts and reuse the groups that are defined there for all your other actions you want to do later in the provisioning stage. So while we quite use Ansible with Azure in production, we are not, or there are some points where we are not that happy about it. It does not work with the latest client libraries, so it's always a little bit behind. Microsoft did the initial implementation of the Azure Ansible module, but there's not a real open source community around it. So until now, I'm not sure if, or let's see how it will further evolve. Defining resources within Ansible is okay for simple tasks. For complex tasks, it's better to switch back to the resource templates and just call the template via Ansible. The dynamic inventory was really helpful for us, and we pretty much use it, and it works. And so now we kind of have a hybrid approach where we use the JSON templates to define all our infrastructure and inject the parameters via Ansible. So that's a rough overview of the deployment, how we use Microsoft Azure. As I said earlier, if you have any questions, you can ask them now or just meet me at the conference. Thanks.
Hi. You said you were planning to shift to Azure and then start shifting up into the high-level services. I wonder if you've got an idea yet of what those high-level services you're thinking of shifting to are.
For example, until now we use only the simple blob storage, but we want to migrate to the HDFS services that Azure provides. At the moment, we are deploying our Postgres databases at our own. Microsoft Azure has an on-demand service for Postgres services, where if you automatic backup and automatic upgrades and all this stuff. So that are two examples where we want to go up in the stack. And even something like they have a full managed Hadoop service, where you don't have to care about deploying the stuff. That's also an option.
Thanks for your talk. I was wondering, how do you authenticate your tools like Ansible or like any other script you have against the Azure API?
Yeah, basically we have a GitHub repository with all our deployments installed there. We have a requirement txt file, and that's what everybody uses. And once we want to migrate to a newer version, we do a branch and then update the versions, deploy it to the test environment and see if everything works, and then roll it out to the other stages.
Yeah, but you mentioned role-based access control, and I was wondering, like, how do you, for example, give to a developer less privileges than other developers? Do they use individual accounts, or do they use specific access keys?
No, we have a sync tool. We have an internal Active Directory, or it's an open LDAP server, and we've written a sync tool where he syncs the permissions that are in our internal, the groups and the developers to Azure, and then we have some labels attached to each group or developer, and that's the way we manage the role-based access.
Is that via ADFS that you show in a slide?
Sorry?
ADFS, Azure Federation Services?
No, we have that's a separate tool. We just use the API to sync our users inside. Okay, then thank you.
Hello, how's it going? Well, next speaker is Will Foster, and he's from Dublin, Ireland. He hides under a principal system engineer job in Red Hat, but he's fooling everybody. Will's really a comedian. Will is going to introduce the so-called quads, so let's give it a charm applause.
Buon pomeriggio, ragazzi. Tutto lo talk in Italiano. Allora, this talk will be in English, thank God, because my Italian's terrible, as you can tell, and I apologize if I've offended anybody in the audience just now. So my name's Will Foster. I'm a DevOps engineer at Red Hat, and today I'm going to be talking about an exciting new Python-based framework called Quads that we've developed in-house that solves some of the problems that we have. And I'm just going to get right into it. So before I kind of explain what Quads is and how we've built this sort of framework to solve some of our infrastructure and automation problems, I want to explain what I do at Red Hat. I'm on a very small team of 2 people, and there's not enough car analogies on the internet. In fact, there's never been a car analogy used for open source. It's never happened. So I'm going to use a car analogy here to kind of explain what I do and what my other colleague does on the DevOps side. So I want to talk about high-performance computer servers as race cars. Very high performance, fully spec, the latest Intel, AMD chipsets as race cars. And high performance networks would be the race tracks. And the race car races that run on these tracks would be performance and scale testing of various open source products that Red Hat develops, and also upstream things like OpenStack and OpenShift and Kubernetes and different types of technologies that we want to test and vet at a very large scale. And the actual race car drivers themselves that are driving these servers that are race cars on these fast tracks, 40 gig, 100 gig networking, or race tracks, are the race car drivers. They're the scale engineers. And that's a pretty cool analogy to have if someone says, what do you do? Well, I drive race cars. So that's kind of, I'm throwing a bone to more of the core performance and scale engineers by calling them race car drivers. But I look at myself and my colleague on kind of the DevOps side as we're the pit crew and we're the track engineers. And our goal is to make as many races happen all the time as efficiently as possible without any wrecks or explosions, and those do happen, which I'll get to. And this tool Quads helps us automate the entire thing, including writing our documentation for us, configuring VLANs on Juniper and Cisco switches, and the full life cycle of provisioning bare metal servers, spinning them up, passing them to an engineering group for product and scale testing, and then spinning them down when they're done. So if this was either a terrible analogy or an awesome one, I have a very simplified one, and this is the Reader's Digest version, which basically we manage 300 or so high-performance servers and switches and a large infrastructure. And this infrastructure accommodates parallel product testing, and it's really comprised of isolated sets of machines. We refer to them as clouds because we're not very creative, for different workloads that happen simultaneously. And with Quads, we have basically automated our entire jobs. We've automated ourselves out of a job, and instead of spending the time going and being network engineers, being systems folks that have to deploy servers, we've automated all of this with Python, and we instead spend our time on actually improving the automation. So what is Quads and what isn't it? What sort of things does it do and not do? Well, it's not an installer. It's not a provisioning system. It bridges several interchangeable tools together. I mentioned Foreman because that is our back-end provisioning vehicle that we use. But we design Quads in a way that if you have an existing provisioning system or a workflow or anything that you're used to, you can plug that into Quads. Quads will simply call out to your provisioning system to do re-kicking machines, re-provisioning machines, or pushing image-based deployments across a lot of servers. And it also helps us automate basically the boring things that maybe you do once or twice and it's exciting, but you never want to do again. You know, I love network engineering, I love connectivity, I like switches and firewalls, but I don't want to do that for a living. I would rather automation do it for me because it makes a lot less mistakes, and it's frankly better at it. But basically, our goal is to build a system that orchestrates and builds all the other systems, and only spend our time maintaining that automation framework and trying to waste as little time as possible being hardware people or being network people or storage people, because you know it gets boring when you do just one thing. So what is quads from kind of a high level? We drive everything with PyYAML. So the top level idea is that for every asset in our infrastructure, we have a YAML-based schedule that tells it what it's supposed to be doing, from what start date and what end date, and what isolated work group or assignment. And this way we can programmatically schedule things in the future. You know, in an ideal world, you would know the development schedule of all of your engineering groups. You would say, you know, in November, Team A is going to be releasing a beta of Project Y, and Team C is going to be doing the same thing. And if you knew what people's needs were ahead of time, you can schedule compute and network resources in advance. The reality of it is none of that ever happens like you would like it to. Deadlines shift, there's different holdups and blockers with bugs and different projects, and how you perceive the world to ideally be is never actually how it turns out to be. So we've baked in a little bit of resilience into how we schedule things in the future. So a little bit more detail about how it actually manages this kind of programmatic YAML-driven scheduling and provisioning. We set aside the YAML schedule for server assets, and then we automate basically the entire life cycle of a set of machines from beginning to end automatically. So on a Sunday at 2200 UTC, if you're going to be receiving, say, 200 servers in what we would call a Q and Q0 or a specific VLAN configuration that we support, automatically your machines would spin up, they would reprovision, the tooling would go out to each of the switches and configure your VLANs, so you would have one isolated environment separate from the other engineering groups, and things like a foreman self-service account would be created, you would have your own IPMI credentials to get into the machines out of band, and then our documentation would be automatically generated to reflect the current state of what your machines are doing and who is using all of the assets inside of an environment. So, like, how do we use this internally at Red Hat? So we have a large R&D environment called the Scale Lab, and this is where we test and vet all of our products. You know, Red Hat Enterprise Linux, OpenStack, you know, Rev, Satellite, just I don't even know how many products we have, but that's where we test them. And it's a very special place because all of the hardware is deemed high performance scale gear. You know, we use 100 gig networking across the board. It's all very high end servers. And it's not a place for you to have a development test bed. It's a place for you that if you are doing development work and you hit what could potentially be a scale issue with any sort of bits of the application stack, and you're able to reproduce this issue on a smaller scale, this is where you go to run it at a very large scale so we can anticipate how customers using our software would do in the real world. Ideally, we would identify issues before other customers hit them, but again, that's not always the case. So in our Red Hat Scale Lab, we have about 300 servers. We have 40 or 50 high-performance Juniper switches. And right now, we run about 16 to 20 different isolated scale and performance workload on these systems for up to 4 weeks at a time. And Quads helps us spin up these machines, hand them over to the appropriate people for short-term lease, and then spin them back down again and put them in kind of an allocation pool. So I'll give you an example. And let's look at some pictures, because everyone likes pictures. So this is the example of some of the scheduling that we do automatically. So this is from February to May of this year. And you can see how we've very efficiently done back-to-back scheduling of all of the machines in the environment. And you can see, you know, 4 to 5 parallel running workloads, testing different products, different scale, different aspects of different products. And all of this, when it's scheduled in advance, all happens automatically. So we don't ever have to waste time. There's a 2-person team. We got a lot of infrastructure. So we don't have to waste time manually setting up any of this stuff, nor would you. Here's an example of some of the metrics that we've gotten from the lab. I kind of picked this at random. This is a storage workload. And these are some of the results that we get out of the Scale Lab, and Quads kind of empowers us to do this sort of work. So we talked a little bit about the time savings and efficiency, but I want to drill down more into what problems we're actually solving here, besides the obvious. So the first one is server hugging. Does anyone know what server hugging is? Okay, so server hugging is the idea. Once I explain it, you'll be like, oh, yeah, I know server hugging. So server hugging is the idea that if you give someone a resource, they're going to hold on to it as long as possible until you pull it back from them. Developers are very bad at server hugging, and usually there's always more of a demand for resources than there are actual resources to give people. So if you're lucky enough that your manager is particularly savvy and he can fight for a budget to have this R&D dev test hardware, and he's better than the other managers at it, then you're going to have more gear to play on. But the sad reality is there's never enough bare metal hardware, unless you're Facebook or Google or one of these behemoths, that you're not going to have bare metal high-end server hardware to run your code and test against all the time when you want it. So server hugging is the idea that there's this tendency of people to hold on to things longer than they should. And it's a natural human thing. You're given something, you want to use it, and you kind of become protective over it. It's your pet, it's your area, it's yours, but it's not really yours. You got to share it with other people. So by having automated scheduling of server resources and network resources, you sort of force people to be more efficient with their planning. You force them to maximize the time that they would have on a set of hardware, and you can save a whole lot of money and time by doing it this way. So what's the other things that we solve when we automate things? There's less human error. That's good with more automation. And to a certain extent, you can kind of give control over to the machines, because what's the worst that's going to happen at that point?
Mass reprobation human.
So there's obviously bugs in Quads, and kill -9, terminate. There's obviously some rough edges in our software, as there are. But the idea is that you automate as much as possible. The biggest area of devastation is on the network side. It takes one typo to configure the wrong port and totally offline a machine, or just cause straight up havoc. So simply just automating the network administration is a huge boon to having errors. The downside is when automation fails, it normally fails in glorious ways. It's normally just a giant explosion, slow motion train wreck when your automation actually fails, because it's so efficient at something, and if that something has errors, then it's going to be catastrophic. So Dave Wilson, if you're watching this, I'm really sorry about your 50 machines that got eaten by our network bug, but it's fixed now. So what are the other things that we're solving here? So we want to maximize idle machine cycles. Electricity is expensive, carbon footprint is always an issue, and we want to automate and spin up machines only when they're
Mass reprobation human. Power off.
Where were we? So what we do is we power off machines when they're not in use, and only when they have an active schedule in their YAML config do they actually come alive and participate in some sort of an automated workload. And sometimes they don't work like you'd like them to. But that's kind of the double-edged sword of automating things. So lastly, we want to solve the scheduling issues. We go with short-term reservation. So if you rent, say, 100 machines, if you use Quads, and you get assigned 100 machines in a particular VLAN configuration to do your development and your testing at scale, the maximum you can keep it is 4 weeks. because we only have a couple hundred servers, but we have queued up almost a month wait time to get to those resources. So we want to be more like Airbnb and less like a hobo house. Airbnb has very defined guidelines. You can't stay in an Airbnb longer than 4 weeks, and it has uniform, for the most part, kind of things you would expect from an Airbnb. You know, you generally know what you're going to get. Maybe not, but it's a little more polished and professional than, you know, like, say, a hobo house. And the last thing that we really save here, and this is kind of the impetus for us continuing for us to automate our jobs and then work on the automation, is the time savings and the cost savings. So we had done some kind of back of the envelope math of using 100 machines, for an example. If 100 machines changed hands tomorrow and went from one development group working on something, or a set of developers with a specific scale or performance problem they were trying to fix, what would be the cost and the time involved if someone was to do that manually? Now, granted, in 2017, I hope no one is doing all of this by hand. I hope people aren't inserting an ISO into a server somewhere and someone's on an SSH console and a switch, and I hope people aren't doing it that way. Maybe some people are. But assuming that you did do everything manually, it would take roughly 90 hours of work to provision 100 servers and pass them off to someone else. So for our current 2-person team, that would be about 45 hours apiece over a week of work. And if we tripled our team, it would be about 15 hours or 2 working days. And if we had a 12-person team, we could maybe get it done in a day. So Quads does all of this on Sundays when most people aren't working, and automates the entire thing in a span of 2 or 3 hours. So when Monday morning rolls around, machines are already passed off, notifications are already sent to the users, they already have their own special credentials to access the machine that only they have, and then the clock starts ticking on the reservation. So I'm not going to drill into this, but this is kind of how we came up with this figure. And these are pretty conservative estimates of everything that we do. All right, so how does Quads actually do all of this? We've talked about the problems that we're going to solve with it, that we solved today. We talked about the level of automation and efficiency that we're able to yield, but how does it actually look on the back end? So I have made some rather grotesque topographical images for you. This is not going to win any website awards, but we all remember Milton from Office Space. We're going to say he's your typical scale engineer, and he needs hardware. So this is the kind of Quads architecture at a very high level. We have now a JSON API in front of it, but generally speaking, there's also a daemon and also a CLI that you'd interact with. At its very basic construct, there is a YAML schedule that is constantly modified by PyYAML. And I'll give you an example of that a couple slides later. But this is at the heart of how things are automated in the present and in the future. There's also some provisioning elements. If we want to do any graphing, we have hooks into Collectd and Grafana. And we also can send results to Elasticsearch as well. But this is more ancillary stuff that we would set up after the fact. Automated, of course. And then lastly, there's the consumable here, besides the actual machines, is the documentation. At any point, anyone can look inside of this Quads managed environment. They can see what all the machines are doing, what does the utilization look like, who has the machines, what are they working on, and for how long they'll be working on it. So when you provide transparency like this, it's easier for people. They don't have to ask you, hey, you got any spare machines, guys? Or I have this project a month from now, what's the schedule going to look like? All this is already published and available to anyone who wants to look at it. So there's tie-ins to the actual provisioning, which is the next slide. And there's a plug-in to Quads, basically a open-ended command that we call move hosts. It's just a simple argparse option in Quads. But this is where you tie in your provisioning system. So however you run the life cycle of re-provisioning on operating system or laying down an image over top of it, whatever your method is, you plug this into the move hosts command. You define this in Quads. It can be whatever you want. In our case, we just use Foreman because that's one of the tools that we enjoy using and saves us some time. So the Quads move host command would basically spit out if the time is running, like if now is scheduled right now for a set of machines to change hands and go to another environment with another VLAN configuration, we would get this printed out in our logs. We would say, this example server is moving from Cloud 01 environment to Cloud 02, as an example. On the back end, on the foreman end, at least for us, this is our provisioning workflow. We would tie foreman in to add and remove role-based access for the host. We would change the IPMI passwords so that users are isolated in their own environment. We would do a full provision of the operating system. We would lay down any post-configuration stuff, and then we would actually move the VLANs on the physical switches, depending on the VLAN design that we support. And then lastly, and I think more importantly, is there's automated network validation that happens. We don't want to pass off a set of machines to people if they're not ready to use or if there's something wrong with them. So we run automated validation that checks and checks and checks, and if every one of the machines doesn't pass the network validation, we get notified, and then it continues to check in intervals until we fix the problem, and then it finally passes validation, and the consumers of the hardware, of the isolated environment, get notified through a couple different mechanisms, usually IRC bot and email. So we talked about the YAML schedule per host. This is what it looks like. This is kind of at its basic, the construct of how the PyYAML drives current and future scheduling of machines and networks. So we see this defined schedule here. The very simple command of ls schedule will list you all of the current, the past, current, and future scheduling that Quads knows about for a particular asset. So at the very bottom here, number 5, that would be like, say, a current allocation. That would be something that started June 28th and is going to end the 6th of July or has ended. And we keep a historical record of this in the YAML file because that drives the documentation and also the visualizations that we make. So, on to documentation. Now, I like writing documentation once. In fact, I don't even really like writing documentation, but it's one of those things that is so critical to any sort of project or any sort of endeavor that it's also the most lacking aspect of documentation. So we decided that one of the pillars of this Quads framework would be to automate all of the things that we either don't want to do or we are going to screw up at some point. If you have even outdated documentation is still better than no documentation, but it's still terrible. So our goal was to have absolutely up-to-date, by-the-minute documentation. And the way that we do that is we query our provisioning source. In this case, it's Foreman. It could be anything else. It could be Ansible Facts, for example. And then we query Quads because it knows about the past, current, and future schedule of everything in our infrastructure. We parse it into Markdown format, and then we use an XML RPC Python library to push it up to a wiki page. And then this is continually updated every minute. Anytime there's a change in the environment, anytime a bare metal server is added or removed, this gets updated in the infrastructure documentation. In this case, we use WordPress. It's got a nice API for this, but it could easily be MediaWiki or anything that supports some programmatic Markdown format. And again, it doesn't even have to be Markdown. It's just that's what we currently use. So this is an example of what it actually generates. So this is the front sort of infrastructure documentation of a set of our servers. And this is what is continually generated and updated over time. We have your typical things you would expect from infrastructure docs, like a host name, serial MAC address, IP address. We have a link to the out-of-band console. But what's different from this than something that someone edits is that on the right-hand side, we have workload. So if you were to click on that workload link, you would drill down to exactly what those sets of machines are doing. What is Cloud 06, for example, doing? We know R. Bryant is the owner of these sets of machines. And then this is an older image, but the graph link would redirect you to a Grafana dashboard that has all the historical bandwidth throughput of all the interfaces per machine, which is useful. And again, these serial numbers are actual servers, but they're out of support, so you're not going to gain anything by getting them from my talk, but you could certainly pay the bill for us if you feel inclined. So, along with a general infrastructure layout of the documentation, we drill down into assignments. Again, kind of what machines are doing right now. And this is just an example, a snapshot taken a few months back of various internal testing of products and things like that. We see a lot of OpenShift stuff in here, OpenStack, elements of OpenStack. We see some software-defined networking running, things of that nature. And then you can drill down further into the workload and you'll see how long they've had the assignment, how long it's going to run, and what's the remaining time. So again, this just gives people an added level of transparency to see there's no more black box. What's going on with this server gear that we have? You know, it's very clear. Is there servers available? I can request them and I'll get them. And then I get this nice generated printout. And then we also tag faulty machines. So if there's something wrong with the hardware, we simply assign a key value pair of faulty, and then it goes into the spare pool or the faulty pool that we can have the local lab people take a look at and fix. On top of the documentation, we have visualizations as well. We generate a calendar, so at any point you can see what kind of tests are running inside of the R&D scale environment. And then lastly, we have a heat map visualization. Now, this doesn't look like it's going to win any website awards. It looks like the old Windows 95 defrag program. Do you guys remember that? Where it's like the big blue grid and then the colors change. But it's incredibly useful from a scheduling perspective because we can look at, and this is generated 3 months in advance, 6 months in advance, whatever you want to set it at. But we can very quickly see what's available from a day of the month or at a longer view, and then we can use that to schedule free servers for people that have requested it. So again, and this is all automated, automatically generated for you. Cool. So as you see earlier, we definitely need more testing, and CI is very important. So we do have testing. It's not good enough, but it's getting there. We use Garrett for code review, and then we use Jenkins for the CI. And we're working on now kind of a fully instantiated virtual sandbox using Open vSwitch and some other stuff to emulate switch ports. But right now, we're using Flake 8, we're using shell check for some of the shell kind of glue that we have in the project, and we need to probably get proper tests in. So we're getting there. Quads is about 11 months old, and it's been running our R&D environment for about 8 of those months. Cool. So what's working right now? This long list of stuff that I'm not going to read to you. This is available in all the documentation that we have. If you're curious, you can ask me after the talk. But it's going to do a whole lot of stuff for you. What are we working on? This is even more important. So what are some things that we have planned to introduce with quads? The major thing right now is we want to introduce the idea of like a post config. And what that would do is, it's one thing to provision the networks, the storage, the servers for people and hand them off and document them and then reclaim them when they're done. But you probably want to automate other stuff on top of that. We have a lot of folks testing OpenStack, for example, and you might get, say 50 servers to do an OpenStack deployment, and then you're testing a specific part of that OpenStack deployment. And you could easily burn 1 or 2 days getting OpenStack deployed and getting just right. So we want to offer the option of kind of an open-ended model that whether you're laying down an infrastructure as a service set of software or you want to lay down some kind of container orchestration on your host, we want to offer the option that is also automatically done for you. So when developers come in on Monday or Tuesday or whenever they want to work, they not only have their servers that are documented, that they have their credentials and they're ready to go, but they also have any ancillary software stacks that they need to test on top of already set up for them. And it's about saving time and being as efficient as possible. We're also working on a Flask web interface for quads to kind of enable some self-service scheduling. So if you're, developer Jane Doe and you want to schedule yourself 100 machines for a week and they're available, you can go to the Flask interface and request them. In a week's time, whenever you want to start, your machines will show up for you in a few hours. So that would be a really cool feature to have. We just put in place a JSON API. So that's been pretty useful, but we're not using it internally, but it does work pretty well. That's going to kind of pave the way for the Flask interface. So we're kind of doing slow moving blocks that way. We just got in place the automated network validation that I talked about. And we also want to support more resource backends besides Foreman. I'd like to have an Ansible backend that all you have to do is run Ansible against a set of hosts. You yield all of the facts from discovery, and then that is what formulates the information that's in the wiki that's automatically generated. So again, you know, the overall theme of quads, of this kind of loose framework that we put together, is being as efficient as possible with the few resources that you do have. And you'll kind of see this. So in our case, and this is really a construct of any sort of company that's larger than 20 or 30 people, if you have bare metal assets, or say you have machines in a data center or rented resources, is that over time, development groups tend to silo their resources. So, like Department A is going to have their servers, and they're going to be entirely different make and model than Department B, and they're going to be bought at a different time, and their depreciation date's going to be different, and maybe their hardware profile is different. So a company ends up spending a lot of money maintaining these little siloed areas and pockets of infrastructure. And the idea behind quads is that you put everything in one giant bucket, and then you let quads do all the provisioning, all of the scheduling, and take care of the whole thing for you. Now, obviously, there's downsides of automated scheduling and provisioning, in that sometimes people's deadlines slip, or sometimes they have something come up and they need to take vacation, or they can't use the hardware. So we've built in things into PyYAML, and PyYAML is very good at this, in that we simply just need to modify the schedule, and then the Quads framework does the right thing from a provisioning perspective. But again, this is a lot of very little tools, little small things that do one thing and do one thing well, sort of sticking to the Unix KISS principle, if you will, that we just keep it simple. And selfishly, from kind of the DevOps operations side, is that we don't want to do the same thing more than once. If it can be automated, we want to automate the crap out of it. If it's boring or we mess it up a lot, we want to automate it. And if it's something that's we just don't want to do, obviously machines can probably do it better for us. So that was kind of the drive to initially get this thing going. So the parts of Quads might be more useful than the sum of its parts. Some people like to use just the automated documentation, for example. The scheduling aspect might be useful. There's parts of the framework that you could consume yourself because it's not all tied together. It's very modular. So we've also got some external interest into Quads as well. There's some ongoing collaboration we're doing with Boston University and MIT in the Massachusetts Open Cloud. So we're kind of merging parts of Quads with their scheduler that they've written called HIL, H-I-L. And we've had some kind of large public companies show interest in using it for their dev and test environments. So that's basically it. Thanks for coming to my talk. If I have any time left, I could open it up for questions, if anybody's got some. And if you want to read more, everything's open source. It's all on GitHub. And we certainly welcome patches because we're just not that good at Python, but we want to be. So welcome for anybody to give us a shout and look at the code. Yes?
Curious that can we use this like the framework for failure testing of a cluster?
For what type of testing?
Failure testing. Failure testing. Failure. I mean, if some of the nodes goes down, can we use to test such a scenario?
I don't know.
Okay.
It's really aimed right now for bare metal servers and kind of scheduling, provisioning, and resources based on a future date.
Okay. For example, what happens if like one of the nodes doesn't start on the scheduler? What happens then? It just logs and you go and fix it by hand?
You're talking about OpenStack specifically, or?
For example, your class writing like the US schedule, like the 50 nodes with your computation.
Uh-huh.
And if one of them fails, what happens?
I don't know. I'd have to think about it and get back to you. Yeah. I mean, you can layer on any sort of post-provisioning automation that you like, and orchestrate that yourself. It's designed in a way that we don't want to dictate a use case for you. We find great utility and efficiency in having kind of an open-ended framework. And if there's certain parts that you can reuse, it's designed in a way that there's inputs for that. So we ship like a YAML configuration file that, just a key value pair that if you want to use a different wiki, for example, or if you don't care about the provisioning aspect, you could only do the scheduling, or you could only use the documentation part.
Hi, thank you for the talk. You mentioned about the way you schedule and provision servers. What happens when they go offline? Say you reserve 50 servers and then 2 of them go offline. Do you have any logic in terms of preparing them, spare servers? What's exactly the policy on a large-scale setup?
As far as
You
error?
reserve 50 servers, right? And 2 of them go offline. It happens. Servers break all the time. So how exactly do you manage that in a company policy? Assume they technically won't be servers anymore. Do you provision them from somewhere else?
Well, so things are going to always break. You know, you can build in any level of validation of pre-provisioning validation, but we found when you're doing very large deployments, like several hundred servers at once, there's going to always be 1 or 2 stragglers where, you know, maybe they don't PXE correctly to Kickstarter. Maybe there's a failed disk that isn't picked up by the monitoring system. So the best that we can do is bake in as much automated validation as we can. And right now that's only on the network side, but we don't really do it on the system side. Generally, we have enough servers that if there is a serious hardware failure, we can easily shuffle them out of the pile and throw another one into the mix, and then that one takes its place. And then we can always sort it out later. And then that's why we generate the faulty servers on the documentation. But I don't know a good solution for that, because you're fighting against so many factors at that point inside of a data center. There's the network layer, you have power issues, you have anything you could even think of that's going to go wrong at a large scale. So we build more, our redundancy is more built into having at least 1 or 2 spare of that type that we can quickly shuffle in and then dealing with it later, rather than trying to bake in extremely long, tenuous validation. But we could always do better on the system side validating. Does that answer your question? Great. Yes, sir.
I'm just wondering about the network side. How do you actually deal with connecting out to your devices, say your Juniper, your Cisco? Do you have any issues with like vendor interoperability and how you connect? Do you use just like NetMiko or something, or?
I'm sorry, can you repeat?
So do you have any issues with interoperability? So Cisco, you might connect to it via SSH, or
right, yeah.
With Juniper, you might have a better way, like a NetConf or something.
We do. Certain vendors, because we have a pretty heterogeneous environment. We have a lot of Supermicro machines, a lot of Dell machines, and they're not made equal when it comes to, you know, out-of-band interfaces and things like that. So we do have to do some one-off things. It's more apparent on the network side that you would interface with Junos completely different than you would interface with iOS. So we have per vendor tooling that would go out and change the VLANs, and everything is done. We basically keep this flat file structure, and it's done in some kind of a CSV format. So there's one per server that has several fields, and it maps, like, say, the Ethernet interface to a MAC address, and there's a field there for vendor ID. So if we were dealing with a Cisco switch versus a Juno switch, we would need to make sure that that vendor ID field actually has Cisco. And then if it does, it knows to use the other tooling that does the equivalent iOS stuff. But it's not elegant in any way. It gets the job done. Ideally, and this is more of a immediate future thing, is that Ansible is working on network orchestration, but it's done at an abstraction layer. So you would have Ansible drive all of your switch changes, but you would tell it, I don't care what the vendor is, I want this VLAN or this construct to go from this to this. And if it's in its desired state, it does nothing. So it's idempotent, but you don't need to care about the vendor semantics. The abstraction layer in Ansible will take care of that. But I don't know how baked that is. I think it's very actively being worked on. and that's what we're going to move to. But right now, we maintain per vendor network automation scripts. And luckily, right now, we're almost all Juniper across the board, so it makes that easy. But any other questions? Well, feel free to find me after the conference, and you can borrow my Terminator mask and attack me if you like. I'm into that, I guess. So thanks for your time, and I appreciate you coming to the talk.
All right. So next up, please give a warm welcome to Nikola Jipanov, who will give us a presentation on how Facebook uses Python to build and operate data centers at scale.
Thanks everybody. Hello. My name is Nikola Jipanov, and I'm going to be telling you about how we at Facebook use Python to help us build data centers at scale. Some of you may remember me from previous years from such venues as the River Bar. I'm a production engineer at Facebook. Production engineering as a role is kind of like a mix between software and systems engineering. I'm not going to talk about this in a lot of details now, but if you're interested, you can swing by our booth down at the marketplace and we can tell you more about this. So this talk also has an alternative title, which I'm sure is a theme that you've heard a lot about in this conference. Still, and it's automating the things that you didn't think you could automate. So Facebook is growing really fast. We have more and more users doing more and more things on the site. This means that some things that we could get away as a company by doing by hand, we can't do anymore because we're not going to catch up with the requirements of our scale. Now, I'm not saying that this applies to any company out there, but an interesting thought experiment would be if you consider that computers are getting cheaper, it's actually getting more and more expensive every year for you to not use computers to do things, because humans are not getting cheaper, in theory. So yeah, this may not apply to everybody here, but at Facebook, we really needed to stop and think about how we can stop doing things that really are not going to scale. And this is one story of such a thing. So, a fabric. This is how Facebook designs data center networking. This is the so-called spine leaf topology. I think it's a design that somebody came up with in the 1950s, so at the bleeding edge of technology, as always. And what this allows us to do is add compute capacity without having to mess with the network, among other things. I'm not a networking expert, but we do have some networking people here at the conference, so if somebody's interested in this particular thing, you can again swing down by our booth, and I'm sure some of the networking folks will try to help you. And interesting data point is that there are networking people at the Python conference. So yeah, that's kind of like part of the whole theme. Yeah, so but at Facebook we actually have, we have many of these fabrics because we have a number of regions that have a number of buildings in them, so this adds up quickly at Facebook. So a question for the audience and a little bit of a nausea-inducing animation thanks to PowerPoint is how much fiber cabling connects all of these fabrics? Like maybe venture guess. Let me just say that for astronomy nerds in the audience, this is not an actual representation of planetary motion. Just to, get it out there. So it turns out there's quite a lot of fiber cabling in our data centers. Some of my colleagues from the data center teams calculated that it's about 1 million kilometers of fiber cabling that we have to deal with. So it's in theory enough to, in this make-believe universe, go to the moon and back and around. So we can think about this in terms of fiber ports. that we have to deal with in our data centers. And as we are adding more capacity, we have less time to do the things we used to be able to do without automation. And we can't do that anymore because there's just more stuff happening. Today we are at approximately between 10 and 20 million ports, but that number is going to grow in the next couple of years rapidly. Yeah, so this is really not where we want to be. When it comes to operating this stuff, we also don't want to have people deal with this kind of stuff. We need to do better. And then cheesy animation. Later, we built robots with funny tattoos to help us do this. And one of the tattoos is a Python logo. So it's on the slide. Yeah, so this is a nice sunset, California sunset photo of, I think it's building 16 in the main Facebook campus in Menlo Park, California. The address is 1 Hacker Way. And this is kind of like what we at Facebook believe is a good way to solve problems is to hack. So we hold these hacks, which are also kind of like hackathons. They can be a couple of days long. Nowadays, mostly people go home and sleep. I don't think this was the case all the time, but nowadays it is. And we take this very seriously. Lots of engineers take a couple of days to think about exactly the kind of things that I try to talk about here, like what things can we do better? And then maybe sit in a room for a day or two and try to come up with a quick prototype. And many internal projects and even external-facing products at Facebook started out as like crazy ideas that people just sat together in a room and hacked on for a day or two. Yeah, this is an aerial shot of the campus. Building 16 is at the top right corner, I think, and you can see the San Francisco Bay at the back. Like, realistically, you cannot just hack your way through some problems. You can start out like that, and that's a good way to build a prototype, test your ideas, but as you want to use this and make better use of it, you have to put it in proper production. And there's one language that's actually quite good and helpful when you need to come up with a fast prototype, but actually it works well in production as well. You've probably heard about this language, but yeah, at Facebook we're kind of like thumbs up in Python. Here's some numbers from our one single repo that we have that I pulled out to June. These are rough numbers, but we actually have thousands of binaries running in production. A decent number of them is Python 3. We have millions of lines of code. 40%, if you look at the line of code count, is actually Python 3, so we are very invested in Python 3. And it's the second most used language for backend services after C++. Like most people probably know that like the front end of Facebook, the product, is written in slightly improved or a significantly improved version of PHP, so we don't count this here. But everything in the back end is mostly C++ and Python, with some other interesting bits here and there. So how does it all work together? You have all of these servers running Python, C++. Some people like Haskell. It's apparently cool, or used to be. At Facebook, we use Thrift. Apache Thrift. It's basically an RPC framework. And what it does is like, you can define types and you can define the interface of your service. And then you have a compiler that compiles this and generates language-specific code. So you can have services written in different languages that can talk to each other seamlessly, and all of your definition lives in like a file like this. So this is obviously a very contrived example. This is not actual code, but like our system to help us deal with a lot of fibers would maybe have an interface like this. You would define a fiber type and maybe define a location type, and then you would have a fiber server, and then you would be able to ask what kind of fiber cabling is happening at a certain location. And then, like, once you run the Thrift compiler and generate some code, then you get generated code, which you can then import, and it's fairly easy. As you can see, there's only like about 6 imports. Then you have to actually write the business logic of your service. That's, we still haven't cracked that problem. I mean, how not to do it. And then you instantiate your handler. There's a processor. There's some kind of, there's 2 factories because one is enough. Just generally, this is not very engineer friendly, and it's also, there's a number of problems with this. Like, there's no signal handling, there's no monitoring, there's basically nothing. So we came up with a solution to this and open sourced it. It's called Sparts. It's basically a services framework for Python. And at Facebook, we use Thrift for everything. So it supports Thrift, but it also supports HTTP, and it does a lot of cool things. You have periodic tasks, background tasks, you have logging, command line arguments, all sorts of nice things like that. So even if you're not interested in using it as such, it's very nice readable code, so you can take a look at it. If you're interested, like, this is a good example of how you would write a service framework in Python, which I'm sure like is becoming more and more common nowadays. And then if we use Sparts, this whole boilerplate becomes much better. There's just, you still have to write your code. We can't help you with that yet. But then it's just like a couple of things. And this thing will do way more than the previous example did, because it will expose metrics so you can monitor your service and go on like 5 weeks of vacation like Hinek did, and all sorts of other things that you get for free. So for those of you who were paying attention, I did mention binaries before, and most people think of Python as a interpreted language, which does not have binaries. It has source files that are then interpreted by the CPython interpreter. At Facebook, we actually don't use virtual env pip or any kind of thing like that. We actually do build binaries, and we distribute them to all of our machines also using Python, which I will tell you more about this in a moment. So we have one build system to rule them all in Facebook. It's called Buck, and it's also open source. So if somebody's interested in this, you can go to buckbuild.com, and you will see. You can read more about Buck. And basically, we use Buck to build Python binaries. This is not the new technology. Like, this is done. There are open source solutions to this. But what we do is, like, we put it in a zip archive and then prepend it with a shell script that knows how to extract and execute the code. So all of our code, all of the binary dependencies, all of Python, pure Python dependencies would be in a one big blob that you then send to all of your servers. Buck can help you with a lot of other things. It caches your build artifacts so you don't have to rebuild things all the time that don't change. And it has a very nice reproducible way to define your builds. And if you take a look at this, this is actually also Python code. So this was actually very useful for me to come up with all the stats from a couple of slides back, because you can use things like the AST module to parse this and figure interesting things out about your build. So in this case, we define our thrift library, which tells which tells Buck to build and generate the generated code, and then we have a Python binary that depends on this library and runs server py, which then solves all of our problems, in theory, of course. So yeah, like I said, now we have binaries. Facebook, we use BitTorrent, which is also powered by Python and async IO, to take those binaries and distribute them to a huge fleet of servers where they need to be. So, yeah, Python is heavily abused. And this leads us to the kind of like the TLDR of the talk. And if you take anything away from this, it's, well, actually it's two things. Some things about how we use Python at Facebook, but also that the robots are coming, and I was really practicing this, but I couldn't come up with a good enough impression of an Austrian accent saying, "and they need your clothes." So imagine I said it in an Austrian accent. But yeah, like I said, as things scale, you need to automate more and more things. I think this has become a very big theme in a lot of talks that I heard today and the previous days at this conference. So it's something to think about. For me, it's very interesting to think about how really a lot of things that you didn't even think you could be automating are starting to, pieces of it are starting to get eaten by computers and done by computers more and more. And at Facebook, we use hacks. It's a very fun, interesting way to come up with ideas of what things can go away and be done by robots. Yeah, and with that, I ran a little bit short on time, but we're hiring, and what's interesting for these folks, I think, is London and Dublin offices for production engineering. So if you're interested to come and build robots with us and maybe do cheesy slide decks, yeah, come to the booth and talk to us. That's it. Thank you. As for questions, I would prefer if people grab me at the booth. I'm going to be at the booth whole day tomorrow, so I think it's a little bit awkward to talk like this. So come grab me after at the booth, and we can chat. Thanks a lot.
A big hand. We're then going to take a quick break. The next presentation starts in about 15 minutes. Hello, everyone. Next up, we have Tracing Fast and Slow, digging into and improving your web services performance. Please give a warm welcome to Lynn Root.
Hello, good afternoon. Does anyone actually get the reference in my title? Like, I see like 2 or 3. Yes, so it's a reference to a really awesome book, Thinking Fast and Slow. I highly recommend it. No relation to this actual talk though. So yes, my name is Lynn Root. I am a site reliability engineer at Spotify. I also do a lot of open source evangelism internally, and you might know me from PyLadies as well. Also, unfortunately, I'm going to take up the whole time. So if you have questions or want to chat, you can come join me for a convenient coffee break right after this. Okay, another quick question. Has anyone read the Site Reliability Engineering book, aka the Google SRE book? I think I see a few hands. All right, well, I highly recommend that book, but the TLDR of every chapter seems to be use distributed tracing. So with the prevalence of microservices, where you may or may not own all the services that a request might flow through, it's certainly imperative to understand where your code fits into the grand scheme of things and how everything operates with each other. So there's 3 main needs to trace a system: performance debugging, capacity planning, and problem diagnosis, although it can help address many other issues as well. So while this talk will have a slight focus towards performance debugging, these techniques can certainly be applicable to other needs. So I have a bit of a jam-packed day today. I'll start off with an overview of what tracing is and the problems we can try to diagnose with it. I'll also talk about some general types of tracing we can use and what key things to think about when scaling up to larger distributed systems. And then the inspiration for this talk stemmed from me trying to improve the performance of one of my own team's services, which sort of implies we don't really trace at Spotify. So I'll be running through some questions to ask and approaches to take when diagnosing and fixing your service's bottleneck. And finally, I'll wrap up with some tracing solutions for profiling performance. And as I mentioned before, I won't have time for questions, so you can catch me right out there. All right. In the simplest of terms, a trace follows the complete workflow from the start of a transaction or a request to its end, including the components that it flows through. So for a very simple web application, it's pretty easy to understand the workflow of a request, but then add some databases, separate the front end from the back end, maybe throw in some caching, have an external API call, all behind a load balancer, then scale up to tens, hundreds, or thousands of times. It gets kind of difficult to put together workflows of requests. So historically, we've been focused on machine-centric metrics, including system-level metrics like CPU, disk space, and memory, as well as app-level metrics like requests per second, response latency, database writes, etc. Following and understanding these metrics are quite important, but there's no view into a service's dependencies or its dependence. It's also not possible to get a view of a complete flow of a request, nor develop an understanding of how one's service performs at scale. So a workflow-centric approach allows us to understand relationships of components within an entire system. And then we can follow a request from beginning to end to understand bottlenecks, hone in on the anomalistic paths, and figure out where we need to add more resources. So when looking at a very simplified system where we have a load balancer, a front-end, back-end, database, maybe an external dependency to a third-party API, and when we have redundant systems, it gets particularly confusing to follow a request. So how do we debug a program of a rare workflow? How do we know which component of this system is the bottleneck? Which function call is taking the longest? Is there another app on my host causing distortion of machine-centric metrics, performance metrics, something like the noisy neighbors problem? So with so many potential paths that a request can take with potential for issues at each and every node and edge, this can be mind-numbingly difficult if we continue to be machine-centric. So end-to-end tracing will allow us to get a bigger picture to address these concerns. And looking at the magnitudes of what we're operating at Spotify, you can see that tracing, if we did it, would help us a lot. So real quickly, there are a few reasons why we trace a system. The one that inspired this talk is performance analysis. This is trying to understand what happens at the 50th or 75th percentile, the steady state problems. And this will help us identify latencies, resource usages, and other performance issues. We were also able to understand questions like, did this particular deploy of the service have an effect on latency of the overall whole system? Tracing can also clue us in on anomalistic request flows, the 99.9 percentile. The issues can still be related to performance, or it can help identify problems with correctness, like component failures or timeouts. Profiling is very similar to the first, but here we're just interested in particular components or aspects of system. We don't necessarily care about the full workflow here. The fourth one, we can also answer questions of what a particular component depends on and what depends on it, particularly useful for a complex systems. So when, with dependents identified, we can also attribute particularly expensive work, like component A adds significant workload with disk writes to component B, which can be helpful when attributing costs to teams and service owners or component owners. And then finally, we're able to create models of our entire systems that allow us to ask what-if questions, like what would happen to component A if we did a disaster recovery test on component B. So there are various approaches to tracing. I'll only highlight 3 of them here. The first is manual. It's also very simplistic, where you are just generating your own trace IDs and adding them to your logs. And there are very simple things that can be added to your web service here, especially ones that do not have dependent or depending components that you don't have access to. You won't get any pretty visualizations or help with centralized collection beyond what we typically have with your logs, but it still can provide insight. So this is a Flask example, super simple, using a decorator. Here you can simply add a UUID to each request received as a header, then log at particular points of interest, like at the beginning and end of a request, and then any other in-between components or function calls where you want to propagate headers. And this is exactly what I ended up doing for my service, which made me wish for a better way, hence this talk. I must admit I do a lot of conference-driven development. So if your app is behind Nginx that you're able to manipulate, you can also turn on its ability to stamp each request with an X request ID header, as you see here with the add header and proxy set header. You can also add a very simple, you can simply add the request ID to Nginx's logs as well. Next up is black box tracing. This is tracing with no implementation across the components. It tries to infer the workflows and relationships by correlating variables and timing within already defined log messages. So from here, relationship inference is done via statistical or regressional analysis. And this is easiest with centralized logging, and if there's somewhat of a standardized schema to log messages that contain like an ID or a timestamp. It's particularly useful if instrumenting an entire system is too cumbersome, or you can't otherwise instrument components that you don't own. And as such, it's quite portable, and there's very little to no overhead, but it does require a lot of data points in order to correctly infer relationships. It also lacks accuracy with the absence of instrumenting components themselves, as well as the ability to attribute causality with asynchronous behavior and concurrency. Another approach to black box tracing can be through network tapping using SFlow or NFDump or IP table packet data, which I am sure the NSA is quite familiar with themselves. And then the final type of tracing is through metadata propagation. And this approach was made popular by Google's research paper on Dapper. And so components are instrumented at particular trace points to follow causality between functions, components, and systems, or even with common RPC libraries like gRPC, and that will automatically add metadata to each call. So metadata that is tracked includes a trace ID, which represents one single trace or workflow, and a span ID for each and every point in a particular trace, like a request sent from client, a request received by server, server responds, and then the spans start and end time. So this approach works best when the system itself is designed with tracing in mind, but not many people do that, right? So this avoids guesswork with the inferring causal relationships. However, it can add a bit of overhead to response time and throughput. So the use of sampling traces limits the burden here on the system and the data point storage. Sampling anywhere between 0.01% and 10% of requests is often plenty to get an understanding of a system's performance. So when starting to have many microservices and scaling out with many more resources, there are a few points to keep in mind when instrumenting your system, particularly with the metadata propagation approach. So in terms of what to keep in mind, and I'll go into detail about each in a second, we want to know what relationships to track, essentially how to follow a trace and what is considered part of a workflow, how they are tracked. Constructing metadata to track causal relationships is particularly difficult. There are a few approaches, each with their own fortes and drawbacks. And then how to reduce overhead of tracking. The approach one chooses in sampling is largely defined by what questions you're trying to answer with your tracing. And then there may be a clear answer, but not without its own penalties. And finally, how to visualize. The visualizations needed will also be informed by what you're trying to answer with tracing. All right, so what to track? When looking within a request, we can take 2 points of view, either the submitter point of view or the trigger point of view. So the submitter point of view follows or just focuses on one complete request and doesn't take into account if part of that request is caused by another request or action. So for instance, the evicting cache here that was actually triggered by request 2 is still attributed to request 1 since its data comes from the first request. The trigger point of view focuses on the trigger that initiates the action. Where in the same example, request 2 evicts cache from request 1, and therefore the eviction is included in request 2's trace. So choosing which to follow depends on the answers that you're trying to find. For instance, it doesn't really matter which approach is chosen for performance profiling, but following trigger causality will help detect anomalies by showing critical paths. All right, how to track, or essentially what is needed in your metadata. This essentially boils down to, it's very difficult to reliably track causal relationships within a distributed system. The sheer nature of a distributed system implies issues with ordering events and traces that happen across many hosts. And there might not be a global synchronous clock available, so care must be taken when deciding what goes into crafting the metadata that is threaded through an end-to-end trace. So using a random ID like UUID or the XRequest ID header will identify causal related activity, but then tracing implementations must use some sort of external clock to collect traces. And then in the absence of a global synchronized clock, or to avoid issues like clock skew, looking at network send and receive messages can then be used to construct causal relationships, because you can't exactly receive a message before it's sent. And a lot of tracing implementations use this very simplistic approach. However, this approach lacks resiliency. There's a potential for data loss from external systems or inability to add trace points to components that's owned by others. Tracing systems can also add a timestamp derived from a local logical clock to the workflow ID, where this isn't exactly the local system timestamp, but either a counter or sort of a randomized timestamp that is paired with a trace message. So with this approach, we don't need the tracing system to spend time on the ordering of traces it collects, since it's explicit in the clock data, but parallelization and concurrency can complicate understanding these relationships. And then one can also add the previous trace points that have been already executed within the metadata itself to understand all the forks and joins. It also allows immediate availability of the tracing data itself as soon as the workflow ends, because there's no need to spend time on collating or establishing the order of causal relationships. But as you can imagine, metadata will only grow in size as it follows the workflow, adding to the payload. So it basically boils down to this. If you really care about payload of requests, then a simple unique ID is your go-to, but at the expense of needing to infer relationships. You can then add a timestamp of sorts to help establish explicit causal relationships, but you're still susceptible to potential ordering issues of traces if data is lost. You may add the previously executed trace points to avoid data loss and understand the forks and joins of a trace, while gaining immediate availability of trace data since causal relationships are already established, but then you suffer in payload size. And then there's also the fact that there are no open source tracing systems that actually implement this last one. So end-to-end tracing will have an effect on runtime and storage overhead no matter what you choose. For instance, if Google were to trace all web searches despite its intelligent tracing implementation, it would impose a 1.5% throughput penalty and add 16% to the response time. I won't go into very much detail, but there are essentially three basic approaches to sampling. First is head-based, which will make a random sampling decision at the start of the workflow, and then will follow it all the way through to completion. The next one is tail-based, which will make the sampling decision at the end of the workflow, implying some caching going on here. Tail-based sampling needs to be a little bit more intelligent, but is particularly useful for tracing anomalistic behavior. And finally, unitary sampling, where the sampling decision is made at the trace point itself and therefore prevents the construction of a full workflow. So head-based is the simplest and probably most ideal for performance profiling, and both head-based and unitary are most often seen in current tracing implementations. I'm not quite sure if there's a tracing system that actually implements tail-based. All right, what visualizations you choose to look at depends upon what you're trying to figure out. So Gantt charts are popular and definitely quite appealing, but it only shows requests from a single trace. And you definitely have seen this type before if you looked at the network tab of your browser's dev tools. When trying to get a sense of where the system's bottlenecks are, a request flow graph, aka a directed acyclic graph, will show workflows as they are executed, and unlike Gantt charts, can aggregate information of multiple requests of the same workflow. Another useful representation is a calling context tree in order to visualize multiple requests of different workflows. And this reveals both valid and invalid paths that a request can take, best for creating a general understanding of system behavior. So what the takeaway here is, there's a few things we need to consider when we trace a system. You should have an understanding of what you want to do, what questions you're trying to answer with tracing. And certainly there will be other realizations and questions that come from a trace system. For example, with Dapper, Google was able to audit systems for security, asserting that only authorized components are talking to sensitive services, but not without understanding what you're trying to figure out. You might end up approaching your instrumentation incorrectly. The answer to this question will help identify the approach to causality, whether from the trigger point of view or from submitter point of view. Then another important question, how much time do you want to put into instrumenting your system? Or can you even instrument all parts? This will inform the approach that you use to tracing, be it black box or not. If you can instrument like all the things, or at least some of it, it then becomes a question of what data you should propagate through an entire flow. And finally, how much of the flows do you want to understand? Do you want to understand all the requests? Then you should be prepared to take a performance penalty on the service itself, and then you can have fun storing all that data. Or is a percentage of the flows okay? And then if so, then how do we approach sampling? And that's in your answer of what we want to know question. So for understanding performance, head-based sampling is certainly fine. You also need to think about whether or not you want to capture the full workflow of a request or only focus on a subset of the system. And this will also inform your sampling approach, be it unitary or not. And so in terms of performance and understanding where bottlenecks are, you want to try and preserve the trigger causality rather than submitter, as it shows like the critical path to that bottleneck. Head-based sampling is fine, as we don't need intelligent sampling, and even with very low sample rates, we can get a good idea of where our problem lies, since we essentially care about the 50th or 75th percentile. And finally, a request flow graph here is ideal, since we don't care about anomalistic behavior. We want information of the big picture rather than looking into particular individual workflows. And so most often, once you are tracing a system, the problem will reveal itself, as will the solution, but not always. So I do have a few questions to ask yourself when figuring out how to improve a service's performance. First one is, are you making multiple requests to the same service? Round-trip network calls are expensive, and perhaps there's a way to set up batch requests or accept batch requests on your end. Perhaps your service doesn't need to be synchronous, or it unnecessarily blocks. For example, if you're some big social networking site, can you grab a user's profile photo at the same time that you pull up their timeline while you try and grab their messages at the same time? Is the same data being repeatedly requested but not cached? Or maybe you are caching too much, or maybe not the right data? Is the expiration too high or too low? What about your site's assets? Could they be better ordered to improve loading time? Can you minimize the amount of inline scripts, or maybe make your scripts async? Are there a lot of distinct domain lookups that add time with DNS responses? And how about decreasing the number of actual files referenced, or maybe minify and compress them? There's a bunch of stuff that can be done with the front end part. And then finally, perhaps you can use chunked encoding when returning large amounts of data. Are you otherwise able to have your servers produce elements of a response as they are needed, rather than trying to produce all elements as fast as possible? All right, now probably the most interesting part. About current tracing systems that are out there. So there is an open standard for distributed tracing, allowing developers to instrument their code without vendor lock-in. And they do this by standardizing the trace span API. One criticism I have of open tracing is that they don't prescribe a way to implement more intelligent sampling other than a simple percentage and setting priority. There's also a lack of standardization for how to track relationships, whether submitter or trigger. It's pretty much all submitter. And it's mainly just a standardization for managing the span itself. But mind you, it's a very young specification that's evolving and developing as we speak. There are a few self-hosted popular solutions that do support the open tracing specification. Probably the most widely used is Zipkin from Twitter, which has implementations in Java, Go, JavaScript, Ruby, and Scala. The architecture setup is basically the instrumented app sends data out of band to a remote collector that accepts a few different transport mechanisms, including HTTP, Kafka, and Scribe. So with propagating data from a service, all of the current Python libraries only support HTTP. There's no RPC support. And Zipkin does provide a nice Gantt chart or waterfall chart of individual traces. And you can see, you can view a tree of dependencies, but it's essentially only a tree with no information like latencies or status codes or anything else. Using PyZipkin, on which other libraries are based, you can define a transport mechanism, like I did here with HTTP transport, which can be just simply posting a request with the content of the trace. You can otherwise make one for Kafka or Scribe. But then otherwise, it's just a simple context manager being placed wherever you want to trace. Jaeger is another self-hosted system that supports open tracing specification. It comes from Uber. Rather than the application or client library reporting to a remote collector, it reports to a local agent via UDP, who then sends out traces to a collector. Unlike Zipkin, which supports Kafka and Elasticsearch and MySQL, Jaeger only supports Cassandra for its storage. The UI is very similar to Zipkin with really pretty waterfall graphs and a dependency tree, but again, nothing to help aggregate that performance information we're interested in. Their documentation is also horribly lacking, unfortunately, but they do have a pretty decent tutorial to walk through. Their client library for Python is a bit cringeworthy. So this is a trimmed example from their docs, just meaning to give the gist here. Basically, you can initialize a tracer that the open source or that the open tracing Python library will use, and create a span and a child span with context managers. But their usage at the end of time.sleep for yielding to IO loop, it's a bit of a head scratcher. Its docs also make mention of supporting monkey patching libraries like requests and Redis and Eurolib2. So all I can say is use at your own risk. After I presented this at PyCon a couple months ago, like the day after, they created an issue and basically made a comment in their code reasoning why, but I still don't get why. So there are a couple others I'm not that familiar with, including AppDash and Lightstep. And there are a few more that don't have Python client libraries yet. And in case you don't want to host your own system, there are a few services out there to help. There's Stackdriver Trace from Google, not to be confused with Stackdriver logging. So unfortunately, Google has no Python or gRPC client libraries to instrument your app with, but they do have a REST and RPC interface if you feel so inclined. But they do support Zipkin traces, where you can set up a Google-flavored Zipkin server either on their infrastructure or on yours, and have it forward traces to Stackdriver. And they actually make it pretty easy. I was able to spin up a Docker image and start viewing traces within a couple minutes. Annoyingly, they have a storage limitation of 30 days, same with their logging. And my last criticism is their UI. They have simple plots of response time over the past few hours, and a list of all traces that are automatically provided in the UI, but you have to manually make analysis reports for each time period that you're interested in to get all the fancy distribution graphs. They're not automatically generated, unfortunately. And then finally, Amazon also has a tracing service available called X-Ray. I only set up their demo app, but it looks like they do not explicitly support Python, only Node, Java, and .NET apps. But the Python SDK, Boto, has support for sending traces to local daemon, which then forwards to the X-Ray service. And what's nice about X-Ray, despite it being proprietary and not open tracing compliant, is you're able to configure sampling rates for different URL routes of your application based on either fixed requests per second or a percentage of requests. However, it's not possible to configure these rules with Boto. Also, or almost redeemable, is their visualizations. So while there's the typical waterfall chart, they also have a request flow graph that, where you can see average latencies, captured traces per minute, and requests broken down by response status. So basically, AWS and X-Ray seems pretty cool and probably the most useful out of all of these, but it'll take some time instrumenting your app and introduces vendor lock-in. And some honorable mentions that do app performance measurement. I don't have personal experience with these, but Datadog and New Relic might be of interest to some of you. All right, and a quick opinionated wrap-up. Got like a minute here. If you run microservices, you should be tracing them. Otherwise, it's very difficult to understand an entire system's performance, anomalistic behavior, resource usage, among other many aspects. However, good luck. Whether you choose a self-hosted solution or a provided service, documentation is all around lacking. Granted, very young space, very much growing as open tracing standard is developing. And as I mentioned, language support isn't 100%, even if it might not even be there. And there's a lack of configuration for relationship tracking or intelligent sampling and available visualizations. But it is indeed an open spec that can be influenced, or you might feel so inclined to implement your own, to which I say good luck. And then finally, all of this and some pretty graphs and stuff is up on my blog post if you're interested. Thank you.
Thank you, everyone.
I'll see you folks out there if you have questions.
test.
Seconds.
So, I think we can get started. Our next speaker is Stefan Wirtel. Stefan, you've probably seen around the conference. He's part of the EuroPython team and also organizes Python FOSDEM and is a fellow of the PSF. And Stefan is going to tell us how you can integrate best practices into your existing Django project. Stefan?
Hello. Yes, I'm just Stefan. My name is Wirtel, but I like Stefan, just that. This talk is just about firstly, it's a real pleasure to present my experience to you because sometimes I don't like to expose something. Firstly, it's my first talk about Django. I'm not a fan of Django. I prefer Flask. But because I signed a contract with Django, for Django, but I started to use Django. I'm not an expert, just a newbie, a beginner. If you have some advice you can give me, you can send me your message. About the rest, well, yeah. Yes, only develop some backends, web services with Python, of course, and Sync.io, maybe with Golang or Erlang. It's my biography. On the left is just a draw of my daughter. You can see there is a big snake on the center. It's me, I'm a Python lover. Of course, I use open source, I develop open source. Open source is just my life since 20 years. And I just created the Python FOSDEM. You can come for the next year. And what else? Yeah, I am a member of the PSF, of EPS. I receive CSI from the PSF because I just created the Python FOSDEM. Yes, just that. So, for presentation, I need a use case. And in this case, in this talk, sorry, I'm going to use the EuroPython website, okay? I appreciate the work which has been done by the current developer of EuroPython website. We know EuroPython is just an awesome project. We are there. That's really awesome. Because without EuroPython or PyCon, Python is not the fabulous project. Thank you. So this event has been organized by some people, and these people, the organizer, are the main developers of Python, of EuroPython, sorry. We have some work groups in EuroPython. We have the financial group, the support group, and of course the marketing group. And there is the web team group. I am in this work group. My first contribution to the website was in 2015, sorry. I'm not French, I'm not English. And when I have time, I contribute to the project. But when I have time, and maybe that's the main reason why I'm not a big contributor. But this year, just explained that I signed a contract to be a Django developer. Okay, normally I am a Python expert, and I know Flask. Maybe Django is not very difficult, okay? So, if you want to read the source code of EuroPython, the website, you can go on this address, okay? Of course, you can contribute. So, EuroPython, the website of EuroPython is not just a facade. It's not just a small site where you can see the speaker or just the attendees and the rest. With EuroPython, we can do the conference management. We can manage the tickets for the assign, unassign, or just orphan tickets. You can come. We can do some statistics about the attendees, the speakers, and the rest. We can also make the invoices or just the refunds. Oh, I cannot come. Can you refund me? Okay, maybe. When you send an email to the support because you have an issue with one person or because you have another problem, whatever, there is the help desk. And this help desk will use the EuroPython site. Sometimes you receive some notification by email. We don't use any other system, any external system. We don't use AWS or just MailChimp. But sometimes, and you don't know that, but with the last version of EuroPython, we can do the booking for the rooms, for the hotel, and of course for the SIM cards. But we try to remove this card because it does not work. But yes, we can do that. So, the website, EuroPython, is a really good tool because it's not just a simple website. It will handle the invoices, the refunding, and the rest. But sometimes we need to do the state of the union. Firstly, we use Python 2.7. The support will stop in 2020. And we use Django 1.8. No? Okay. The last migration to the Django 1.8 has been done in the last year, during the last EuroPython. We use some dependencies, but these dependencies are just broken with the new version of Django, or there's no maintainer. That's very boring. Of course, we use SQLite. Sorry. The best is just after. We have no test. Can you start? Come back? Yeah. We have 100 or 200 files and 27,000 lines of code. And no test. And no documentation. Sometimes we can read, you can check in the source code, the commands are just in Italian. Adesso posso parlare un po' italiano, sì. We are just some English speaker, I try, and we understand English, or French, or Italian for, okay. Sometimes we can see in the source code of EuroPython some parts of the code is just duplicated, or we can see some dead code. Why? Because during the migration from the last, sorry, for the history, the previous version of the EuroPython site was based on the PyCon Italia site. That's the reason why we have the commands in English, in Italian, and they use several applications. With the new version of EuroPython, we just merge them, okay? And that's the reason why we have some duplicated code. Of course, no asynchronous, no continuous integration, sorry, and no API for the external tools. In fact, we have nothing, okay? But, and no syslog, of course. Yes, the settings are hard-coded. I think we have a problem. But seriously, I think we are not alone in this case, because I'm a freelancer. with Python. And when I go in some companies, I can see the same case. No documentation, no continuous integration server, in fact, nothing. Yes, it works, okay, sure. But don't forget one thing. Because we are at EuroPython, EuroPythons are started in 2002, and since the beginning, we have a lot of former developers. In reality, 31 developers. Secondly, we are some volunteers on the free time. Just that. We are not paid for that. It's not the case for the companies. And we are not web dev, just data scientist, backend dev. We try to fix the issues. Okay? From that, I think we have a real challenge. Maybe a small, maybe a big, but we have a challenge. The first challenge is to have a continuous integration server. Okay, we can install GitLab, we can use in GitLab, or maybe Travis. We will see that in the future. We need documentation, not in Italian, maybe in English. Why not in Flemish? But English is better. For the configuration, that's very important, because currently the settings are just hard-coded in the source code. That's very boring when you want to move from the production to the staging to the production server. That's very funny. We need some tests. Maybe refactoring the dead code, remove them. Of course, improve the quality of the code, just that. That's very important. The profiling. Sometimes we develop some application with Django, but we don't use some tools, some funny tools. We need to improve the deployment. I don't know for you, but I need some companies, they copy some script from a wiki, and they passed all the lines in a shell because they don't know Fabric, Ansible, or SoulStack. And we need to monitor everything. The website, is responding or not, the database, there is a shutdown or not, everything. About the continuous integration, we have good news. I have good news. I started to use Travis, just the configuration. It's not really difficult. Okay? For the documentation, what's the best project? Who wants? Maybe Sphinx. I like Sphinx because we have the syntax and we can extend it. And because we have a lot of plugins for Django. About the configuration, we can start to change the source code and just use Django.env. .env is just a small file where you put your configuration. You can see that in the part of the top, where you give the configuration for PostgreSQL, for the secret, for the debug environment, and the rest. And in the bottom, it's just lines of code that you have to put in your manage.py. That's very funny. With that, you don't need to change your configuration with the settings.py. I have seen some developers, they comment the source code, the settings, and try to use the other part. For the test, please, just please, use unit test or PyTest. Don't try to make your own framework. I see that. That's very funny. It's just... I use PyTest, and I'm going to show you that because there is a funny, a good project, PyTest profiling. But please use a framework. It's a basic requirement. And don't believe that your code is just perfect. We are humans, and the human make a lot of error in this life, of course. So when we create some test, how to create a test? We create a function for the test, and after we implement the code. But with a legacy code, it's not the case. You have the legacy code, and you have the test. You want to try to write the test. Maybe you can write the test in function of the code coverage of your application. In this case, you can use coverage. or just if you are using PyTest, pytest.gov. That's true just for the source code, but sometimes you are using some templates. And in the templates, you are not sure that your template is just used with the right function. Example, you want to add a new parameter to an endpoint, and you have to check all the templates. Okay, you can try to create a test for each template, but there is a plugin for that, Django Coverage plugin. This small plugin will analyze the template. It will give you just a small report. Okay, there is an error in this case, just that. Because we use the version 1.8, since this version, the migration engine of Django will execute all the migration file. And sometimes that's very boring, but with a big B, because the test will take 2 seconds and the migration 2 minutes. With just this plugin, we can disable the migration. When you try to write your test, that's just more important, that's better. For the rest, we have some models, I suppose. Who use the fixture? Bad. Sorry. Yes? That's bad. Why? Because we have a static file. And when we update the model, we had a new field. You have to update your fixture. I don't know for you, but in the companies where I work, they try to implement a small script where it will put some values for the new field. In my case, I just use factory boy, create a factory for the model, and from that, I can implement a new instance of my model. Just when you write the code, or when you want to refactor your code, you can use PyFlake or just PyLint, just some linter, where they tell you where you have an error in the source code. For example, you just forget to declare a variable. You use a variable, but this one is not really, it's not in the source code. When you develop, you can use Django PDB. When you have an exception, automatically PDB will start, it's a post-mortem, but automatically it will start on this line where you have the issue, the exception, and you can start to debug. Don't use print. Print is just for the beginners, it's my case. If you are using PyTest, I'm going to use PDB PP, because PDB or IPDB just does not work with PyTest. Of course, because I'm a contributor of CPython 3.6 and 3.7, I like to use MyPy. And we can use MyPy. MyPy is just a small tool where we can check the source code. We can create an analyze of the source code and give a report where, okay, this variable is just a string, but you want to assign an integer. It's not correct. And MyPy can give us a report where we have the duplicated code, or just the duplicate function. We can use Autoflake. Autoflake is just a tool where it will remove the unused import files from the source code. And for the import, you can use isort. Isort will, in function of your configuration, will sort the import file by 3 groups. For example, for the standard library, for the standard library, the external library, Django and whatever, and your own library. Okay. Maybe Django debug toolbar. Do you know how they debug or profile an application with Django in my team? Before I was the lead. They take time, they start time, and they make the difference between the start and the stop. Just that. But we don't know the number of queries in the database, And about the CPU, we have nothing. It's really interesting. I use it. I don't know for you. When you run the server with run server, you can use Django, Django Dev Server, and the line profiler plugins, where you will get a small report for the profile of the profiler. And for each line, we will get the result for each line. Okay, this line takes 2 minutes or 2 seconds, sorry, and the next line will take 1 millisecond. That's very important. Yes, for you. PyTest profiling. PyTest profiling is just a wrapper around C profile, but it has 2 interesting features. The first one is just profile SVG. With this feature, it will create an SVG file and will generate the lines where you can see, you will have a file, a prof file, where you can execute a tool to show you a graph with the duration, the calls, the number of calls, the times in the application. And you can use the second parameter, just durations. Duration will write a report where you have, in this case, just the 2 slowest functions in your source code. I like that, because sometimes we can have this graph. I don't know for you, sometimes you have a function, you think it's a CPU bound, but in fact, maybe there is a problem with this NKO, with the DIO. In my case, that was just a problem with my network. So I'm going to continue with the profiling. We can use cProfile V. cProfile V is just a web interface for the prof files. You can see just a small screenshot where we have all the stack trace and the calls for each function and the times. Just need to install it with pip install. So for the deployment, we're using Docker, and we use Docker Compose. But maybe in the future, I would like to use Kubernetes or Docker Swarm, because if we implement a new feature, we want to see it before to put it in the production server, because we are some developers. For the monitoring, I would like to use Sentry, because currently we receive an email, just an email, and we have no statistics about this exception, nothing. Sentry is really a good tool for that. Maybe use Supervisor D, or just Kubernetes or Docker Swarm, because it can restart if there is a crash of the process. And for the rest, Nagios or Shinken. So, next point is just the state of the onion after this refactoring, because I did it. I have added Travis. We have some tests, 97 tests. It's not really big, but it's not better than 0. We have code coverage, 32%. 32% on 27,000 lines of code, that's good. In 1 week, I think it's good. Started to port the database to PostgreSQL. The source code started to be compatible with PostgreSQL. And of course, sometimes I use the profiling because I have observed some difference with the speed in function if we use SQLite or PostgreSQL. Next step, just add the documentation, remove the dead code, move to the last version of Django, Django 2.0 or 1.11. I prefer Django 2.0 because we will remove the support of Python 2. Of course, use Python 3.6 because we have some improvement, and mainly with the last version of Python 3.7, in some months. Use Postgres because Postgres is Postgres, just the perfect database for me. Use Celery. Maybe we will provide some API because currently, you know why the schedule in your application is not synchronous? synchronized with the website, because every day we just export the schedule from the database to the application. And maybe create a single page app. So, there is an expert, a Django expert in the room, because maybe we need your help. Because we are volunteer, we don't have a free time, we are not paid for the EuroPython site, it's just on the free time. But maybe you have a better experience than me. How to contribute? During this weekend, we will do a sprint code. Please, come on. Please. I don't want to be alone, okay? Please come. Join the web team. And if you are better than me, please share your best practice. You have a survey, you can go, just read it. It's tinyurl.com/Django-best-practice. And if you have a question, there's a moment. Who has a question? This talk is just my experience in 1 month. Okay? I never used Django before. I don't know if I had the right practice for the project, but in my case, because I already used some other tools in the past, just use these tools. Okay? No question? Yes, just one. I'm in time.
Oops. Hi there. So first, you can run PyTest with IPDB, just -s or -- capture equals to no, which won't redirect the std out, so everything's working with PyTest and IPDB. And second, have you considered, the whole team, to use at least some Django CMS or Wagtail as base on top of which you can build the conference thing?
For the second question, we use Django CMS.
All right.
For the first, sorry, can you repeat?
There was a slide that you said you cannot run PyTest with IPDB because you get some strange event loop error.
But when
you can with a certain flag.
Maybe you can show me, because when I started to use IPDB with PyTest, I don't know why, but sometimes I get some error in my console. But if you have a solution, I'm ready to.
Maybe the tests were failing, but yeah, we'll fix it.
Okay. Another question?
All right, I think we've got time for one more.
I'm sorry?
We've got time for more questions. So, all right.
As far as eliminating dead code, there's a very good tool called Vulture. It doesn't catch absolutely everything for obvious reasons, but it does catch an awful lot of stuff. It does static code analysis on the code base. So that should be useful.
Can you show me? Because,
yeah.
Hey, come on.
All right, do we have a question that is a question?
Yeah, there is Vulture. Just forget to explain it. But yeah, it's a good project also. Thank you. Okay. You come?
All right, our next speaker is Patrick, and he's going to tell us how you can use GraphQL in your web applications. Okay. So give him an applause.
Hi everyone, welcome to my talk. Who am I? I'm Patrick, and you can find me online with Patrick91 almost everywhere. And I work at a web agency which is called Think Studios. We do website for clients, and also we have internal projects. We mainly use Django, but it really depends on what we are building, so we change technologies quite often. But yeah, we try to use new technology as soon as possible because it's good to keep up to speed with the new stuff that's going on the web, especially on the front end. So the modern web, as web developers, we have seen the evolution of the web. So from static website to website with small interaction to website completely interactive. And one of the best practice is to use REST APIs for the communication between the client and the server. But yeah, REST API are good, but sometimes you need something that's better than it because there are some issues. One of the most common issues is too many calls. So for example, imagine that you have an API that gets the user with an ID. You get something like this, which is fine, for example, if you only need to show the username. But if you need, for example, the friends' names, you need to do a call for all of the user. And this is, as you can imagine, is not good, especially for the user experience of your application or website. So one solution is to create a new endpoint, which is user with friends, which will return the user with the friends, and so on. But then you need also the avatar for the user. Then you create another endpoint. But in another page, you just need the username and the image in the avatar. So you create another one, and so on and so forth. And then this is only one case, but imagine if you have many endpoints, it's going to get really bad. So another solution, like a workaround that you can do, is to return everything that you can get from that resource. For example, you can return the user with the friends and the avatar, but then you're sending too much data, you're wasting bytes. And it's not, again, it's not a good experience for the end user because you are wasting their money, actually, especially in a foreign country. So you send too much data in this big block. One solution is GraphQL. GraphQL is a query language created by Facebook around 2012, but has only made open source like 2 years ago, around 2015. And they say in their specification that GraphQL is designed to build client application by providing an intuitive and flexible syntax and system and so on. This is really complicated for me. And I never read the specification because I always saw the example, which is something like this. This is GraphQL. GraphQL is a query language where you can specify from the client what you actually need. For example, in this case, you are asking to get the user name, email, and the friend's name. And you get, when you do this call, you get something like this. So you only get what you actually need, and it's really easy to use. But one of the most powerful feature, and I guess also one of the most liked feature, is typed. So everything in GraphQL is typed. So basically, your schema is going to have typed. For example, for your previous query, you have a user type. You just got a name, an email, there are strings, and they are always there, as you can see from the exclamation mark. And then you have a list of friends. And friend is another type, which is going to have probably name and email as well. Then another feature is introspection. So basically, every GraphQL endpoint is going to expose some metadata so you can get all the types. For example, in this case, you can use graphical, which is an IDE in browser. So it gives you how to complete on your API and the arguments and the fields. So for example, it's getting the product with ID 2, the name, description, and it's getting the picture with size 500 and so on. So right now I've shown you the query, which is basically the way to get data with GraphQL. But also you need to change the backend data, for example. Like with REST APIs, you do post request, patch request, or deletes. So with GraphQL, you always use one single endpoint and one single HTTP web, which usually is post. To change data, use mutation, which is a way to mutate data on the server. And then you also have another operation type, which is subscription, which is similar to the query, but you subscribe to the updates to it, which is you usually use WebSockets. So a query is done, it's like this, as I showed. You have some fields, and you can have also some arguments. So for example, in this case, it's going to get the human with ID 1000, the name, the height with unit of foot. But this is only a shorthand for the query. The actual, the extended version of the operation, the operation is this one. So basically, specify the operation type. As I said, you can have query, mutation, and a subscription, and maybe in the future they can extend the specification. Then you have an operation name, which is basically used mainly for debugging, so you get logs on the server with that. And you also have some variable definition, which include the type that you define, and then you have the selection set. And when you run this query, you get the data that you ask for. But yeah, this is a Python conference, so you want to use this with Python. To use this with Python, you just use Graphene, which is a library that implements the GraphQL server. So you install it, and then you can just import like this. You import the library, you create a class of query. In this case, I'm creating a class which just got only one field, which is hello. And then for each field, you create a function which is called resolve underscore the field, and you can return what the field is gonna return. And also you can use the arguments and do some magic stuff. And then you can create the schema from the query, and you can execute the query. But yeah, this talk is mainly about Django, and there is an extension to Graphene, which is Graphene Django, which is similar to Graphene, but it's got some nice features for Django, if you already use it. To use it, you install like this, and then you have to extend the installer apps with Graphene Django, and then you have to create a main schema, which needs to be specified in the settings. My convention is to use a folder called API and a schema file, and inside the schema file will be the schema, which is being imported from all the other applications. Then you have to add the GraphQL view. In this case, I'm adding the GraphQL view under GraphQL/GraphQL, and also I'm enabling graphical, so I can debug the API without doing any code. And then use like this. If you have an ingredient model, you can just import it, and you can create an ingredient type with the Django object type that's provided by Graphene Django, and it's going to create all the fields for you, so you don't have to do any resolve functions. You can still do it if you need to do some custom stuff, but it's done for you if you don't need to change anything. Then you can create a query where you have to specify the query set. And this is something a bit tricky, because since you can do nested fields with Graphene, you need to be careful that you're not doing n+1 queries, because it's going to be bad on the performance side. So you can check the fields that are needed, and you can do select related or prefetch related if needed. And then you create the schema from the query. So one of the problems that we had at work is to have authentication on the API. And basically, since we are using Django, and it's really easy to do authentication, GraphQL in this case is just a Django view, normal view. So you can use any method that you like. For example, we were using JWT tokens, but you can also use session tokens if you don't have a single web page application, if you're only using GraphQL to enhance some part of the website. And yeah, you can use any Django stuff. Then you have the permission. This is a different paradigm on doing query. So for the permissions, you basically, you don't really have permissions models, but you have permission on the actual fields. And which is, I think it's really good, because you can say, for example, if I'm logged as a super user, I can see the user email. And if I'm logged as a standard user, I can only see the username. But if you, for example, need to have integration with REST framework, for example, you already have an API, this is something that is not working right now. And I made a pull request that you can have a look at it if you want. And you can also use it. I'm using it on one of the projects I work because I need mainly some use cases to test it and see if there is any bugs. Basically, what I've done is to you can use Graphene Django with Django REST Framework serializer, so you don't have to specify the serializer again, especially for the mutations. Yeah, then I would like to touch on a bit of the security, because since you can do nested fields, some malicious user can do like big queries. So for example, they can have like 100 level of nesting. And so one of the solutions that I think it's been adopted by GitHub, which is using GraphQL in production, and also it's public, is to just limit the number of nesting that you can have. And for example, if the nesting level is more than 10, they just stop the query, because it's probably something that's a bit strange. And also you have long queries, because since you can also specify arguments, maybe you can end up with a query that's going to take too much time. And I think Facebook is doing something like this. Basically, they have a timeout on the query. When the query is going to take more than 1 second, they just drop the query and return nothing, which I think is what we should do, because 1 second is already too much. So this is the backend part. For the front end, as I said, you can still use any client that you like to do post request to the web server, but there are two main libraries that you can use for doing queries, GraphQL queries. One is Relay, which is on your right, and basically it's a library developed by Facebook. It's only for React, so if you use React, this is probably the best solution because it's supported by Facebook. But the only problem is that the development is led by Facebook, so they do stuff only if they like. But it's really good. And the other solution is Apollo, which is I think it's community-based, and basically they have clients for vanilla JavaScript. If you don't use any framework, they also have clients for Vue.js, React, I think also Angular and some other one. I was really fast on this talk, sorry. So gonna touch a bit on the front-end part. I don't have slides, but basically with those tools you can do, there are some other features that I haven't told about GraphQL, but some of those are, for example, fragments. So you can have like some components that depend on other data. So you can only do one query, including the components, and then you get everything with just one query. For example, if you have an about page, and then you have, for example, the username and in one place, and for example, you have the user friends in another page, you can combine the query from those components, and it's going to do only one query. And also, one of the issues is caching. Since you are doing post request, you cannot cache. You cannot use something like Varnish or pure Django caching because you are doing post request. So one of the solutions that's been implemented by both Facebook with Relay and Apollo is to use client-side caching. So Apollo is really good at this. Basically, when you do a query, it's going to cache the results for you. So if you do that query again, it's not going to call the server. It's going to just return the data. And other solutions could be to use to analyze the query that you're doing and do cachings on those ones. But it's a bit harder than just pure REST APIs because said you're just doing post calls. And probably this is going to improve because GraphQL is quite new, but like a lot of companies are using it in production, like Facebook, of course, Shopify, and GitHub are the main ones, and they're really pushing it to the limits, and they're also contributing to the spec, which is really good. So yeah, that's my talk. If you have any question, please feel free to do it. And yeah, thank you.
Hey, thank you for the great talk. So my first question is how you deal with pagination using GraphQL.
Sorry, how do you pagination?
How do you paginate? How do you deal with pagination?
Oh yeah, there is one of the ways using, basically Relay has come up with that sort of pagination system. So as I said, you can specify the arguments in the query. Let me see if I can find it. Yep. So in this case, for example, I'm specifying the ID, but you can also specify, for example, the start and the end. And I think, yeah, Relay is doing something, it's using like edges. So basically, instead of returning the list of the user, in this case, we return a list of edges. So you can get the IDs and the start ID and the end ID. Maybe if you chat with me, I can show you some example, because without code, it's a bit hard to understand.
Thank you. And my second question is, while using Django REST framework or some kind of a RESTful approach, you can really easily specify which endpoint is public and which endpoint is private. Can you do this via GraphQL, because you have only one endpoint, and can you specify that this data is public and this data is not public?
Well, the answer is yes, but I don't know how to do it, because I didn't have to do it. But I was watching a talk on GraphQL by GitHub. Basically, they're doing something like this. They have two ways to do this. The first one is, since they have the API is public, and they can also, for example, you can, with your application, you can log as a specific user. They have permissions. They check, before even doing the query, they check the fields that you're asking for, and they check if this field can be accessed by the current user, then they run the query, otherwise they throw an error. And the other one is the schema. The schema is public usually. So basically, when you expose like some fields, it's going to end up on the query, on the schema definition. And they have some metadata on some fields that basically they say, oh, this field is only for internal use. So when they are logged as GitHub, they can see that field, but when you're using as a public user, it's not shown.
All right, thank you. Any more questions? Yeah.
Thank you. You said that a lot of companies use GraphQL already. For Django, Graphene, did you take any open source project as reference to see their problems, how they handled it, or would you recommend any open source project to look at?
Sorry, can you...
Just starting with Graphene and all this stack, would you recommend some open source project as reference?
Oh, yeah. There was a Star Wars API, which was done in Python and Django REST framework, I think, and there is the same for GraphQL. So you can just Google for SW API or SW API GraphQL or Star Wars API GraphQL. That's one of those.
All right, we had one more question right here.
You mentioned mutations. Do you have any example, or could you talk about how these mutations are done through the query?
Yeah, I have an example. Just give me a second. So basically, mutation is pretty similar to a query. So. I have to remember where I've done it. It's probably in a second. Okay, that's a mutation. Basically, you specify the operation name, then the name of the mutation, which is used on the server side mainly, and then you specify some inputs. In this case, I have an input which is called input, and then this is the type. As I said, I'm using JSON with token, and one of the reasons why I did the prerequisites for the annotations for Graphene Django is because I wanted to use this serializer, which does everything for me. And yeah, as I said, the mutation is similar to a query, so you can, you have to pass the input, of course, and then you can get the data, you can specify the data that you want back. That's it. Do you want to see the Django part of this? So, yeah. This is actually it. It's similar to the when you use Django object type from Graphene Django. So you use serializer mutation, and you specify the serializer class, then it's going to create the mutation for you. And yeah, I'm just adding a token field just because I need it.
All right, any more questions? All right, then give Patrick an applause again. And enjoy the lightning talks.